Hi everyone, it's 10 a.m. Eastern on the East. It's 10 a.m. Eastern, so we're going to go ahead and get started. Welcome back. This is day 2 of AI to Assist Mathematical Reasoning. I'm Sam Koretsky. I work on the board on mathematical sciences and analytics at the National Academies. So before we get started, and I'll turn it over to our chair, I'm going to walk everyone through Slido, our Q&A platform again. So throughout the day, we would love to field your questions. So if you're watching the live stream via registering on our website, the Slido should be embedded right alongside the stream, or you can also navigate to slido.com and type in the hashtag AI for Math 23. And through there, you can send in your questions to the speakers and the panelists. And you can also upvote other people's questions, anything that you find most interesting, and we will do our best to answer as many as we can. So with that, I will turn it over to our chair, Petros.
Yes, thank you, Sam. Good morning, everybody. I'm Petros Koumoutsakos. I'm the Herbert Vinokur Professor for Computing and Science Engineer at Harvard University, and I'm also a member of the Board of Mathematical Sciences and Analytics of the National Academies. This is a workshop that was put together in coordination between the National Science Foundation and the Academies, and we prepared an ad hoc committee to organize this workshop and to explore basically opportunities to advance AI to assist mathematical reasoning. So what we are interested to explore is the state of the art. What are the opportunities to advance the current research? What are the challenges and the barriers? And what's the role of the existing and future stakeholders for advancing AI for mathematical reasoning? And I would like to stress also that the workshop will be summarized in a proceedings that will be published in a few months. So without further delays, I would like to turn it over to Heather Macbeth from Fordham University, who will be moderating the first session on building an interdisciplinary community. Heather, over to you.
Good morning. Yes, so this is the first session of the workshop today on building an interdisciplinary community. I'm Heather Macbeth. I'm an assistant professor of mathematics at Fordham University. And our first speaker this morning is Jeremy Avigad. Jeremy is a professor in the Department of Philosophy and the Department of Mathematical Sciences at Carnegie Mellon University. And he is also the director of the Hoskinson Center for Formal Mathematics. His research interests are in mathematical logic, formal methods in mathematics, and the history of and philosophy of mathematics. It's a little bit early, so I don't know if we should directly turn over to Jeremy or to wait for the publicized start of his talk. Sam, is it okay for Jeremy to get started?
I think it's okay. If no one has any objections, Michelle.
Okay.
All right, yeah, let's go ahead and get started.
Okay, over to you, Jeremy.
You're muted, Jeremy.
And a pleasure to be here. I'm going to be talking about machine learning, formal methods, and mathematics, and some of the relationships between those. And here is an outline of the talk. So first, I'm going to talk about symbolic methods and neural methods in artificial intelligence, and argue that for mathematics, we need a combination of both. Then I'll focus on the symbolic side for a bit, and I'll tell you about formal methods in mathematics and relationship to artificial intelligence. I'll talk about some of the differences between mathematics and computer science and the reasons that we need collaborations between the two. And then I'll talk about new opportunities for cooperation and collaboration given the new digital environments that are available. And finally, I'll close by talking about some of the institutional challenges that we face. So in the field of artificial intelligence, there's a long-standing distinction between two fundamentally different approaches. So the symbolic approach is sometimes known as good old-fashioned AI. It's based on logic-based representations, very precise and exact representations and explicit rules of inference. Whereas neural methods are based on distributed representations of data in a neural network. The kind of inferences are probabilistic, they're approximate, and they're based on mining lots and lots of data. In recent years, there's been a lot of excitement about the neural methods. But I think for mathematics, you need a combination of both. So neural methods are good at discovering broad patterns and connections, but symbolic methods are really designed for mathematics to help us get the answers right. So here's a way to think about it. So here I've given a couple of examples of mathematical knowledge and empirical knowledge. So on the mathematical side, there's the statement that if you add up the first 100 integers, you get 5,050. There's a statement of Fermat's last theorem. Some empirical claims that one might make is that it's likely to rain tomorrow, or if the Fed raises interest rates, it's likely to lead to a recession, or maybe that a potential loan applicant will default on a loan. And these are all important types of knowledge. These are all things that one might want to know, but they're different in nature, right? So again, the mathematical knowledge is very precise, very exact. Mathematical methods are designed to give us precision and certainty, ideally. Whereas, empirical claims, they're probabilistic. They tend to have categories with, fuzzy boundaries. So, maybe open slightly what counts as a recession, or there isn't a sharp distinction between kind of rain and maybe a foggy drizzle. And so they're two, fundamentally different kinds of knowledge. One way to think about mathematics is that, in part, what it does is it gives us precise ways of talking about imprecise knowledge. So, for example, you might have a lot of empirical data, and you can extract a clean mathematical model and reason about the model. The model may be only an approximation to a description of reality, and it's only probabilistic. I mean, it's fallible. It's based on the evidence you have. But given a precise model, you can reason about the evidence for it, the evidence that the model is correct, and the implications of the model. And those kinds of representations, I think, are important when we're involved in the reasoning. So when we're called on to think about the consequences of our actions and deliberate and make plans, not just with ourselves, but with others, right? When we're forced to interact with others, we have to state our reasons and give arguments. And that's the kind of thing that mathematical reasoning really specializes in. So on the symbolic side, I'm going to talk about what I call formal methods in mathematics. So the phrase formal methods, it's a commonly used phrase in computer science to describe technology that's used to write specifications for hardware, software, things like network protocols and cryptographic protocols, and so on. And then to verify that these artifacts meet their specifications, that is, that they do what they're supposed to do. And the point is that that same type of technology is useful for mathematics, namely writing mathematical statements and definitions and theorems, and then proving them and verifying that the proofs are correct. So I like to use the phrase formal methods because, again, it is a well-established body in computer science. But when I talk about formal methods in mathematics, you can think of that as being, more or less interchangeable with the phrase symbolic AI for mathematics. And the idea behind it is this: since the early 20th century, we've known that you can represent mathematics in formal axiomatic systems. And what in the early 20th century, this was known in principle. What's changed now is that we can do it in practice. So contemporary computational proof assistants let us write mathematical definitions, theorems, and proofs in a digital, precise form, in such a way that they can be processed and verified and shared and searched by mechanical means. And if you've never seen it before, here's a picture. It's a little bit scary, but this is the Visual Studio Code editor running the lean interactive proof assistant in the background. And the idea is when you're working with this system, what you're doing is you're writing the mathematics on the left side of the window. So there's a statement of a mathematical theorem there. The comments before explain what it's supposed to do, and so on. And then while you're typing, the system is interacting with you and giving you feedback. So on the right side, there's a window that tells you that at every point in the proof, what kinds of objects are available, what hypotheses you have available. And so what this is like a word processor for mathematics. But one that understands the rules of mathematics, can tell you, when you've made a mistake, and also has access to a library of mathematical definitions and knowledge that you can draw on. And so the natural question is, why is this useful for mathematics? And I could probably spend a week, talking about that. But instead, what I'll do is I'll channel some friends and colleagues. So you can find these slides on my webpage. And here is a list of talks over the last few years. Each of them, each of the red phrases is a link to a talk you can see on the web. And these are all instances of mathematicians explaining, why digital technology has been useful to them and important to them in their work and research. On my webpage, you can also find a survey article I've written called Mathematics in the Formal Turn, which again tries to run over the reasons that digital technology is useful. And just to give you a summary of the article, in the article, what I do is I sort of make a list of ways that the technology is useful. So on the surface, the most direct use is to make sure your mathematics is correct. So it's to verify that your proofs are correct and to find and catch mistakes and fix them. But working interactively with the mathematics in this way is a good way of understanding it better and giving you insight into what's going on. It's enabled us in the community to collaboratively build libraries of mathematics, which then can be used as reference and searched for definitions and theorems. It gives us means of reorganizing and tinkering and adjusting and improving our proofs and our libraries and our concepts as well. As I'll describe later, it gives us means for communicating mathematics better and more precisely and working together, collaborating on mathematics. It gives us ways of managing the complexity of mathematics and the mathematical literature. We think that technology is good for teaching. A number of us are using it to teach mathematics to students. We also think that it provides new opportunities for providing access to a broader community of students out there. So people who don't have as much access to traditional mathematical mentorship. It gives them ways to discover and explore mathematics. It also gives us ways of using mathematical computation more reliably. It gives us access to automated reasoning tools, and it gives us access to using artificial intelligence with mathematics. So overall, the technology holds a lot of promise. And specifically, with respect to machine learning and neural methods in AI, applications of machine learning in this domain are entirely new frontier. So to date, there have been a lot of interesting experiments that use machine learning in conjunction with conventional interactive proof assistants, including Mizar, Halllight, MetaMath, Isabel, Cook, Lean, and so on. In these experiments, the machine learning methods and the symbolic methods both play a central role. So, for example, in one recent paper called Draft, Sketch, and Prove, the authors combine neural and symbolic methods. The idea is you use a language. So one approach they explore is using a large language model to first draft an informal mathematical proof. So you give it a statement, you say, give me an ordinary mathematical proof. Then when the system gives you that, you say, okay, please turn this into a sketch of a formal proof in the Isabel proof assistant. And then once you have a sketch of the formal proof, you use symbolic methods, automated reasoning tools, to fill in the details of the proof and verify that they're correct. And so the idea is that, by combining the neural methods with the formal symbolic methods in the background, the formal methods give a clear signal to the machine learning methods as to whether they've actually found meaningful and correct mathematics. And so that gives opportunities for the machine learning to explore, but get feedback as to whether it's being successful. And here is just a picture of the paper you can find on an archive with a list of authors. And one of the things I like about digital technology and the new technologies for mathematics is that it brings mathematicians and computer scientists together. So, the two fields are very different. Mathematicians and computer scientists have different skill sets, they have different outlooks. So mathematicians typically enjoy, thinking about hard problems and trying to solve them, looking for mathematical patterns, finding deep connections between disparate areas of mathematics. and developing powerful new theories and abstractions that help them make sense of mathematical phenomena. In contrast, computer science is largely about implementing complex systems and getting them to work. So computer scientists revel in improving performance, finding clever optimizations, and making very complex systems more reliable and robust. And there are interactions between these two. I think it's important to think of this as a continuum. Mathematicians need to remember that one of the reasons it's so enjoyable to have big ideas is because of all of the things that those ideas enable us to do. And computer scientists need to keep in mind that one of the things that we can do, all the amazing things that we can do, is because we can think about them. We have the conceptual and theoretical scaffolding to make sense of the problems and understand how to address them. So, there needs to be a back and forth between these two outlooks. And what I like about the new digital technology is that these two communities come together. And you see mathematicians, trying to figure out how to implement their ideas and get them to work. And you see, computer scientists learning about mathematics and what mathematicians do and what kinds of tools might be helpful to them. Okay. Okay, so let me talk a little bit about the new technology and how it impacts on cooperation and collaboration. So what we're seeing is, for example, communities of practitioners coming around formal methods and formal mathematical libraries, using social media to ask questions of one another and pose challenges and make plans and coordinate efforts. So, for example, the Lean interactive proof assistant has a social media channel on Zulip. And for a lot of people, it's a way of life. People will just, start it up in the morning and there during the day, things will stream by. And if you ask a question on Zulip, it's very welcoming to newcomers. And if you ask a question there, you often just get, answers within seconds. And if somebody is looking to develop a part of the library, they'll begin with a discussion of ideas and how it should be done. So the liquid tensor experiment, which was discussed in some of the talks yesterday, is a good model of that kind of collaboration. So in that work, it was a large formalization that was kept in a shared online repository. And so participants followed an informal blueprint online that had links to the repository. But while they were working, they were in constant contact on Zulip. So there was a lot of discussion. And as people worked on different parts, it was important to have Lean, the interactive proof assistant, there in the background, making sure that all the pieces fit together. And that enabled people to focus locally on their little subproblems without worrying about how it would interact with the others. And so here is a picture of part of the system that was used. So this is a web interface that was designed by Patrick Masseau. And so there is sort of an informal proof sketch of the proofs and the definitions. But everywhere there are links to formal content. So the check marks indicate the parts that were formalized. And on the web page, you can link to sort of graphs that show you which parts have been formalized and which parts are not, and in particular help you find the frontier, the next files that need to be formalized. Another good example is the port of MathLib, a large mathematical library. So since 2016, the community has been using a version of the system called Lean 3, and now everybody is moving to Lean 4, which is not backward compatible. So it's like translating a million lines of computer code to a new language. And you can ask, how can you possibly go about doing that? But it's been a really remarkable process. So Mario Carnero, who's a PhD student of mine and now a postdoc with me, wrote an automatic translation system that comes close, but still needs user intervention. About 40,000 lines of tactics, so this is small-scale automation in the library, had to be rewritten entirely because the systems were sufficiently different. But then Mario and Scott Morrison led a team of volunteers, and there was months of planning and discussion and a lot of hard work. Meanwhile, while the port has been going on for the last 3 months, contributions of the old library have continued. So there's been a lot of coordination. And there's been just lots of problems with kind of adapting to the differences with the new system. And I think, the way to describe the feel is that it feels like an old-fashioned barn raising. So this is a clip from the movie Witness from a few years back, from actually the 1980s. So Harrison Ford in the movie plays a hardened Philadelphia police officer who has to spend time with the Amish. And in this scene, you know, a young couple has just gotten married and the whole community comes together to build a barn for them. And, you know, what's so moving about it is that it's just how natural it all is. I mean, this is something that's important to the community. And so everybody comes together and everybody figures out what skills they have and what they can contribute. It's something that needs to get done and it just gets done. And the same was true with the port. So here I'm showing you pictures. You know, there were online instructions for people who were going to get involved that, you know, explained how to do it in great detail. There were online dashboards that let people monitor progress and figure out, you know, what needed to be done next. It was, again, constant discussion on Zulip, and every day there were, you know, bots that announced the progress in the port. So it was really, really something that was remarkable to see. And again, it's all based on having this digital technology that supports this kind of collaborative interaction. So finally, the remaining minutes, let me talk a little bit about some of the institutional challenges I think we face in supporting the new technology. I mean, the idea is that, you know, industrial research has to answer to you know, the interests of the corporation that's supporting it. Whereas academic environments are really focused on specialization and departmentalization. And neither one of them is perfectly aligned with the idea of developing technology for mathematical research. In particular, you know, academia is governed by traditional means of assessment. So mathematicians are typically evaluated by experts in the field as the quality of the work, and, you know, publication in respected journals is often used as a proxy for that. Computer scientists are, you know, expected to demonstrate impact, developing technology that has an impact, which is, you know, sometimes judged by the number of citations. In a sense, there's a chicken and egg problem. You know, in principle, mathematicians could get credit for developing useful technology for mathematics if they can show that, you know, lots and lots of mathematicians are using it. But, you know, mathematicians can't really use it unless it's useful to them on solving traditional problems for which they're being evaluated by. Right? So they can't get credit for just kind of exploring and trying out the technology unless it's at a point where they can really use it to make progress on traditional problems. And so both communities need to make substantial investments of time before either one will have anything to show for it. And it's hard to get that off the ground. So, for example, I talked about this MathLib port. The thing about the MathLib port is that for the most part, the people who are doing it are just entirely invisible. I was able to mine this partial list of names from the online repository. So this is a list of some of the people who have contributed to the port. And it's not complete. I apologize to, you know, people I've left out. But for a lot of them, you know, this slide is the only acknowledgement and thanks that they'll get. So I think we really need to think about how to incentivize, you know, once we decide that this kind of work is valuable and important, we really need to think about how to incentivize and reward it. So we need to think about how to incentivize and reward online development of systems and maintenance of systems, development and maintenance of libraries, development and maintenance of systems for collaboration, and all the things that the community has to do to train new users and get them going. Okay, so let me just sum up. I think I'm pretty much out of time. So as I said, the table of contents, you know, we talked a little bit about symbolic methods and neural methods in AI. I talked about formal methods in mathematics, some differences between mathematics and computer science. We talked about cooperation and collaboration and some of the institutional challenges. And here are the take-home messages. So first, progress on AI for mathematics requires input from 3 different communities at least. First, computer scientists working in formal methods. Second, computer scientists working in machine learning. And third, mathematicians using the technology. And I think it's naive to think that we'll make progress, you know, computer scientists can make progress without substantial interaction from mathematicians, because you really need the domain-specific knowledge and expertise. And these communities, you know, are for the most part disjoint and don't naturally interact. But progress is going to require working together. Right? So symbolic methods are good at computation, verification. They're good at the mathematical side. But when it comes to mathematical discovery, they struggle with combinatorial explosion and you know, heterogeneous reasoning. Neural methods can gather, process, and synthesize huge amounts of data, so they can provide insights and sort of big ideas, but they struggle to get the details right. And as I said, we really need mathematicians involved in the process because they have the domain-specific knowledge about how the systems can be made useful for the subject. So to sum up, last slide. So progress in AI needs a combination of neural and symbolic methods. It requires mathematicians and computer scientists working together. Advances in technology for mathematics require new forms of collaboration and interaction, but at the same time, they provide new means and platforms for that. And finally, we need to think about the institutional support for the kind of collaborative cross-disciplinary work that we're going to need to make this work, and ways of assessing the new kinds of mathematical contributions. Thank you very much.
Thank you very much, Jeremy. So I think we need to pass on soon to our second speaker of the session. That's Al-Hussein Fawzi. But maybe a quick question before we do. So I thought it was interesting that you mentioned the new somehow systems for tracking work that were developed by the formalization community in large projects like Patrick Masso's blueprint system, for example. Do you think that there's something for regular mathematicians to learn there, even outside of the use of formal methods?
Oh yeah, no, absolutely. I mean, these are methods that are kind of well-worn methods in computer science and large system development. Computer scientists know how to use repositories and code review and so on. And the interesting thing is now that we're developing mathematics digitally, we're seeing the same types of technology, wonderfully useful, for mathematics. And so in that case, a lot of tools really are ready-made. They don't need a lot of adapting and so on. So these are things. So yeah, I think every mathematician should be using GitHub to collaborate with others.
Okay, so let me pass on to our second talk. So this is Al-Hussein Fawzi. Al-Hussein is a staff research scientist at Google DeepMind. His focus is on AI for science, and in particular on using machine learning to unlock new results in mathematics. Broadly, he is also interested in the reliability of machine learning systems, and in particular in computer vision. Over to you, Al-Hussein.
Okay, thank you very much for the introduction, and thanks for inviting me. So today I'd like to talk to you about challenges and ingredients for solving math problems with AI. So as someone who comes from the machine learning community, so my background is purely machine learning, I'd like to tell you a bit more of my experience in working in a problem in AI for math and the challenges and how is it different from the other problems and some of the best practices. So we're all aware that machine learning has led to revolutions in many areas, in particular in computer vision, in speech recognition, in natural language processing, so many perceptual tasks, but also more recently in playing complex games, like, for example, the game of Go, which was considered as a grand challenge for a very long time, and StarCraft, which has a huge action space, and more recently, helping scientific discoveries, in particular, predicting the 3D structure of proteins from amino acids. So neural networks have been really at the core of this, all these discoveries. And the question is, what about AI for math? So what I will try to tell you in my first part of the talk is try to highlight some of the challenges of applying AI for math problems. As I said, I think this is quite of a different domain compared to the others that I listed, and give you some of the ingredients of that are needed in order to tackle those challenges that are posed by AI for math. In the second part of my talk, I'd like to tell you about the best practices for a collaboration, for getting a successful collaboration between mathematicians and ML practitioners. So to make maybe the what I mean by math problems more focused, so I'll be specifically focused on what I call needle in a haystack search problems. So these are problems where you have a really large search space, and your problem, or the problem consists in trying to find a very rare object in this very large search space. So examples of this include constructing low-rank decompositions of tensors, which I'll be talking about, constructing counterexamples also for conjectures. So let me tell you a bit more about the running example that I'll be using throughout this talk, which is the problem of tensor decomposition. So the problem consists in that you have a tensor T, which is a 3D array of numbers, and the problem consists in trying to find a decomposition into a sum of rank 1 tensors of this particular tensor T. Okay, so in particular, you would like to write T as a sum of UQ times VQ times WQ, where UQ, VQ, WQ are vectors. Okay, and times here means the tensor product, so it's a generalization of the outer product. Okay, and you want to use the minimum number of terms to get to the tensor T. Okay, so this is a pictorial representation of what I mean here. You have your tensor T, and then you want to find this UI, VI, WI that if you sum this UI times VI times WI, get you precisely to this tensor T here. Okay. Now, you might have noticed that this is very similar to the notion of matrix rank, except that we have here a third term, right? We have UQ, VQ, WQ. So in the case of matrices, computing the rank of matrices is, there is a polynomial time algorithm for that. Unfortunately, for tensors, this is an NP-hard problem. So not only is it NP-hard, but in practice, it's also a very, very hard problem in the sense that there are tensors that are of size, for example, 10 by 10 by 10, for which we don't know the rank of, okay? Now, why am I interested in this problem, and why is it important to compute the rank of tensors? Well, because the tensors capture very important objects or like concepts such as, for example, the operation of matrix multiplication. Okay, so as actually like there is what we call the matrix multiplication tensor, which characterizes precisely the operation of matrix multiplication. And then if you do low rank decomposition of this tensor, then you get an algorithm to do matrix multiplication. Okay, and the lower the rank that you find of this tensor, the faster the algorithm for doing matrix multiplication is. Now, why do I care about matrix multiplication? Because matrix multiplication really sits at the core of many other computational tasks, in particular training neural networks, simulation, image processing, and so on and so forth. So really, the idea here is that if we're able to get low-rank decompositions of tensors, then we are able to accelerate a fundamental component and a fundamental component that sits at the core of many computational tasks. Okay, so we've been in our work, we've applied machine learning to this problem, precisely to this problem of computing the rank or computing an upper bound on the rank of tensors, which appeared last year. And I'll be telling you a bit more about what are the challenges that we have found in this problem, but also I think this is something that goes well beyond this problem in what I call like these needle in a haystack problems. So the first challenge I'd like to focus on is the lack of training data. So if we want to train powerful machine learning models, we do need lots of data. So for example, if you want to train an image classifier, you need to have lots of labeled examples. Unfortunately, in math, we do not have so much data that is available. So for example, in the case of tensors, we don't have many tensors for which we know the rank of. But also, like in theorem proving, we don't have lots of theorems that are formalized and proven. Compared to, for example, the shear scale that we have for images. So instead, what we can do is to try to rely on synthetic data, right? So how do we generate synthetic data? So I think many problems in math, and in particular this problem that I just presented on tensors, belongs to what I call one-way problems, in the sense that getting decompositions from a tensor is really hard, but the opposite is actually easy. So what you can do is that you can generate random decompositions and then form the tensor associated to it. Right. So in this way, you get pairs of tensor and decomposition, and you can generate as many examples as you would like. Okay. So this is interesting because you can really carve your, put put the symmetries that you'd like in the data set. So for example, if you'd like to find decompositions that have a certain symmetry, then you can incorporate really these in the training data. Now, obviously, the downside of this approach of creating synthetic data is that the distribution of synthetic data can be far from that of the target that you care about. So for example, if your problem consists in finding decompositions of the matrix multiplication tensor, which is a very symmetric tensor, working with random tensors or having training data as random tensors will usually not generalize to the tensor that you actually care about. Okay, so there is a big distribution shift between the two, between the training and test distributions. Now, this is precisely why in these problems, reinforcement learning is usually needed, in the sense that not only do you consider this training data that you generated randomly, but you can also try to iterate on the decompositions that you found for the target that you actually care about. So in the beginning of the process, you're going to get really bad decompositions, but then you're iterating through this and trying to improve through this using, for example, Monte Carlo tree search, then you can try to get better and better at decomposing tensors. So this brings me to the second challenge, which is, I think, in many math problems, the setup is very different from the typical machine learning setup. So in the typical machine learning setup, we have a training data that we train on, and then we train our neural network on, and then we deploy it, and we would like that the deployed neural network performs well on unseen test data, right? Now, in many math problems, we actually care about one specific instance. We care, for example, about decomposing one tensor or one theorem, and we do have access to the theorem that we'd like to prove, or to the tensor that we'd like to decompose, right? So this is very different from, for example, image classification, where you're going to deploy your neural network, and then you don't know what it's going to be tested on. Okay, so the picture really looks something like this, where you have a training data, so random training data, and then you have this one target tensor that you care about, and you either essentially like are able to solve it or not able to solve it. So this has a significant issue in that there is really not enough diversity in your setup here. So from a supervised learning sense, this, as I said, will not generalize, like the way you train your neural network on the training data, it will not generalize to the target tensor. And if you consider a reinforcement learning setup, then you're going to play the game over and over and over again, the same game over and over again, and you're not able to escape the local minima. So instead, what you can do, and this is extremely helpful, is to consider some diversification operator, where you take the target tensor and then you try to express it in equivalent ways, in such a way that the machine learning model does not know that these are equivalent. Okay, so for example, in this case, you're going to apply a change of basis to the tensor. That's going to change completely the tensor and hopefully get you closer to the training data. Obviously, all these tensors are equivalent, so if you find a low rank decomposition on one of them, then you can propagate back that information to the original tensor. Now, you can even go one step further and say, okay, like even though I care really about proving this particular theorem or decomposing that particular tensor, you can also try to augment that set with artificial or very close tensors that you don't necessarily care about. So, for example, if you consider like the problem of decomposing a certain tensor, then you can consider the related problem of decomposing the tensor in a different field, right? So, if you consider the machine learning setup where you have all these different targets, then what will happen is that this is going to work better for the target that you care about compared to if you only consider that target in the setup. Okay, so what will happen is that you'll have positive transfer between the different targets that you consider. So this also holds for example, different tensor sizes. We noticed, for example, that if you train only on a certain size, you'll not get as good result for this size compared to training on a distribution of sizes. What will happen is that the neural network will identify some techniques for other sizes that then will transfer to the size that you really care about. So the third challenge I'd like to highlight is this idea of performance versus interpretability. So in machine learning, major breakthroughs came from pushing and iterating over performance. So for example, in the task of image classification, the performance improvements were obtained through this, thanks in big part to this competition that was organized yearly on ImageNet. Okay, now this is the same, or like this, the idea of having a yearly competition or a competition every 2 years in the case of protein folding really led to major improvements in the field. So this, as I said, like has been done also for the case of protein folding and led to to AlphaFold 2 in 2020. But this was really progressive improvements that were shown in these competitions. So if we plot an axis where on the one side we have interpretability, on the other side we have performance, most machine learning tasks have been driven by performance. The machine learning models that were designed were specifically trying to obtain a better performance. Now, if we look at math problems, I think by discussing with mathematicians, and in particular with my collaborator, Jordan Ellenberg, I think many mathematicians would agree that most mathematicians are interested in having interpretable results rather than getting the best performance out of the machine learning models. So the problem with this is that we don't have good techniques in machine learning that to try to interpret the decisions that are made by the machine learning models. So we get the result, but we don't really know why the machine learning model did actually this decision. But for math, as I said, this understanding is really key. We'd like to have like in mathematics, we're getting a description or like we're being told how to construct a solution rather than being presented with the solution itself. Okay, so let me give you an example of this. So for example, consider the case of 4x4 matrix multiplication. So what our algorithm or what our neural network has been able to find is this algorithm for multiplying 4x4 matrices, which is better in terms of rank compared to any existing decomposition. Now, this is great for some applications, but for the others, we actually want to know what was the process that generated this decomposition, right? So it's really hard for us to, or for mathematicians to understand what is actually the process that generated this and to read why the neural network did actually these different operations. Okay, so this brings me to the second part of my talk, which is on best practices that I've learned by collaborating with mathematicians. So the first one I'd like to highlight is the idea of partnership versus collaboration. So the first model of a project is essentially to consider a partnership, where on the one hand, we have a machine learning expert, and then on the other hand, we have a mathematician. Okay. Now, what this model, what I'd like to say by, or what I mean by partnership model, is that the mathematician formulates the problem and then asks for an experiment from the machine learning expert. The machine learning experts run the experiment and then it returns the result. Okay. And then you do this several times. Now, I'm arguing that a much better model for the success of the project is a collaboration model, where both parties have a fair understanding of what the other party is doing. Okay, so why is that important? I think this is particularly important because machine learning models, they need a degree of tailoring. If we just use a off-the-shelf model, this is not going to work in general. So we do need to work on it. We need to incorporate symmetries, invariances. So for example, in the case of tensor decomposition, we need to take into account that the rank is invariant under change of basis, reordering of factors, and so on and so forth, right? So if the machine learning expert does not have a good understanding of the mathematical domain, and if the mathematician does not have a good understanding of the machine learning underlying and which symmetries are hard and which symmetries are easy to incorporate, then this is not possible to achieve. The other reason why I think this model of collaboration versus partnership is really important is that as a machine learning practitioner, we do get lots of data. So our experiments generate lots of data. So which actually data to show to the domain expert, how to choose what data to show to the domain expert. So therefore, I think the machine learning expert has to understand what is actually important in this domain. And also, I think quite importantly, to also break the communication barrier, because if we see this as a partnership, then there will be lots of vocabulary that is not understood in communications between the two parties. So maybe like the bottom line here is that time taken for understanding machine learning or math domain is time well spent, especially at the beginning of a project. So the second best practice I'd like to highlight is to establish a progress metric early on and set up a leaderboard. So I think this is really a necessary condition for us to iterate on our models. If we don't have a good objective function or we don't have a good metric of what to actually track, then this is really hard to iterate over models. As I said, there is a huge variety of models that we can use. So we really need to do some gradient descent to really try to achieve the best model. And so this is actually something that happened in the project that we worked in. Whenever so as soon as we set up an automatic leaderboard, then people could try out ideas quickly and score in these ideas. And this led to many improvements in our results. And by automatic leaderboard, I mean that a leaderboard that really connects to the different experiments that the team is running, and so you don't have to manually add each time to the spreadsheet. I think this is a very important idea that is often neglected. Now, the third and last best practice I'd like to highlight is to build on existing works. So there are different ways of building on existing works, and this is, I think, especially maybe talking to the machine learning community, where there is a tendency of really doing things from scratch. I think this is the wrong way of doing things, especially at the beginning of a project. We really need to try to build on existing works. So as I said, there are different ways of building on existing works. So building on top of a theoretical framework. So for example, for finding new algorithms to multiply matrices, we didn't just try to find algorithms in the wild, but rather relied on Strasson's formalism, which uses tensor decomposition. One needs to build on top of successful machine learning models, not try to come up with machine learning models that have not been tested before. So one can, for example, build on successful models like transformers and AlphaZero. And then finally, to build on top of traditional computational approaches. So instead of, for example, trying to design a solver from scratch, trying to incorporate machine learning inside solvers or inside the theorem provers. So I think this is particularly important at the beginning of projects, because this is where we're really trying to check if machine learning is going to be helpful or no. So I think this is like this work of literature review and then trying to build on top of these approaches is really crucial. Okay, so this, I think I'm out of time. So yeah, this brings me to the end of my talk. I'll just summarize the three challenges and ingredients I talked about and the best practices. So the first one in terms of challenges is the lack of training data. I think this is a really fundamental one. One potential ingredient is to use synthetic data, but as I said, this has the issue that it's very different in terms of distribution from the actual distribution that you care about, and so potentially you would need to use also reinforcement learning. The second point is this idea that the setup of the machine learning setup is really different from the traditional machine learning setup. So one needs to really introduce more diversity by augmenting the data. So for example, in our case, to use change of basis. And this third idea of performance versus interpretability, that current machine learning models are not specifically tuned towards interpretability, but more towards performance. In terms of best practices, I'd like to emphasize really this idea of building a collaborative model rather than a partnership model. I think this is really key. To establish a metric early on and set up a leaderboard and to build on top of existing ones. So that's it for me. Thank you very much.
Thank you very much, El Hossein. That was extremely interesting. So maybe one quick question for you before I turn to a general discussion. I was really interested in your discussion of collaboration rather than partnership and the differences between them. So you listed several, I guess, features that you can only get from a closer understanding of what the other domain is doing. And you said, for example, that greater maths understanding can help you incorporate symmetries and invariances. It can, it can help if the machine learning person knows about mathematics because they can filter what they show to a maths expert. I wondered if one issue you'd seen was a question when there was a lot of data about an intuition of which data was sparse and which data was dense. Is this a feeling that can help with the encodings of a problem? I know that Jordi Williamson, for example, spoke about choosing the right encodings, and this seems like a question that needs to be done in collaboration.
Yes, definitely. I think the mathematician should really be involved from the start of the project, in the sense that really the how we encode the data is also a big part of where we can introduce some domain expertise, and we've seen this really numerous times where we were trying to use the trivial representation, but then a mathematician came and then said, oh, but we can represent this in a completely different domain, and it makes it much more concise, and so the machine learning models really love it. So yeah, this is definitely +1 to that.
Interesting. Let me now pose a more general question. This is a point that you both touched on. So I think that both of you had slides somehow drawing out what you perceived as the cultural differences between the maths community and the computer science or AI community. Jeremy had, his slide on finding hard problems and finding patterns versus implementing complex systems and finding optimizations. And Al-Hussein talked about this interpretability versus performance thing. I wondered whether each of you recognized in the other's caricature some truth, or whether you have different opinions there about the cultural differences.
So I thought Al-Hussein's talk was spot on. I mean, so I think the characterizations were quite good. And I think we have to be careful not to make overly blanket characterizations. I mean, there are some computer scientists who are fine theoreticians, and there are some mathematicians who really revel in computational software, for example, and implementing things. But I think there is just a fundamental difference in outlook, and it's interesting, on Zulip, Heather, we see, mathematicians and computer science, they make fun of each other. The mathematicians make fun of the computer scientists for being, naive about what it means to do mathematics and their outlook and vice versa. But on both sides, there's a kind of a deep respect for the very different talents and skills that each bring to the table. So I think, again, I think mathematicians, the focus is on thinking big thoughts, developing new theory, and computer science, there's an emphasis on just getting things done and getting things done efficiently and well. And they're not destroying things, but they're kind of very different focuses, and that kind of changes the way people think and act and go about their daily business.
Yeah, I very much agree with that, and I also agree with Jeremy's characterization. So one thing I think that is often maybe underestimated, even in the machine learning community itself, is the engineering work that is required to make these things work. And I don't know why, but this is usually something that is not really, not considered as something very elegant or something. I mean, this is really a big part of making things work. And like the big projects such as AlphaGo and even the projects working on mathematics, I think 80% or 90% of its success really is due to the engineering work that is being done. This is because, especially that in machine learning and specifically in reinforcement learning, you have a dynamical system. So making the distributed system work is an extremely difficult task. So yeah, I think engineering is not only important, it's really fundamental for these projects work. I agree that math is more about big ideas, but I think that maybe by shifting a bit and coming together, I think we would be able to advance. Not saying that engineering is bad and math is more too abstract. For example, this is the way we see mathematics. yeah, I think there is a way forward like that.
I was very interested by the leaderboard you showed and how you described this process in experiments you'd run, where you first establish a benchmark and then run every different iteration you have of your model against the same benchmark. I mean, this is it entirely makes sense for a machine learning problem. I'm wondering if you can envisage any domain of mathematics at all where some similar model would make sense in trying different things against some common framework. Does that seem like a model we could adapt as mathematicians?
Yes, I think that question is for me, right?
Yes, I'm sorry, I should have directed it to you.
Yeah, no problem. Yes, I think there is a potential, but I think there is, like, one needs to do this work at the beginning of a project, in particular to identify and to quantify what we actually mean by progress. Even that's on the interpretability side. Can we try to actually quantify what this means? Because I think this is really, as I said, this is a necessary condition for machine learning to work. If we don't have this metric, we just won't be able to do any machine learning on top of it. So how, like, whether we can quantify what interpretability means to a mathematician. In some cases, I think this is also, like, there is a natural quantitative metric, for example, the number of theorems proved, or in this particular case that I present is the rank. So in some cases, I think it's just a mixture of some interpretation and some quantitative metrics. So I think weighting these things together and just maybe arriving to one or just a few scalars that we can use to evaluate our different models, I think this is really a fundamental work that needs to be done at the beginning.
I'll actually connect that to a question from Talia Ringer. So she asks, sometimes the machine learning community gets carried away gaming benchmarks that measure the wrong things from a domain expert perspective. So, I mean, this seems very plausible to me indeed. Do you have any stories that you would like to tell of cases where somehow the benchmark was wrong to start with?
That's, yeah, I mean, that's definitely true. Yeah, so, I mean, I don't have now a specific example I can share, but it's very easy if we don't know the topic enough. I think it's very easy to get carried away and saying that, I don't know, like, take a very simple example of, let's say you want to do integer factorization, right? So I cannot factorize n, but I can factorize n+1, right? Does that mean that I'm closing to actually factorizing n? No, that's obviously not the case, right? So so the fact of so the difficulty does not depend essentially on the, or like the difficulty or the benchmark is very much related to the instance that you care about, right? So getting the wrong metrics is definitely something that if we don't have the prior knowledge, we will easily make. So that's why it's very important, and that's why I'm emphasizing that we should really make these leaderboards with mathematicians that are experts in the field.
Yes, this certainly makes sense. Another question from the Slido. So this one is for Jeremy, and I think it's about the question of how to extrapolate from progress in AI for mathematics into progress for AI in other domains. So you made this point that real-world knowledge can be somewhat ambiguous, but mathematical knowledge, for example, tends to be quite precise. And formal systems work well for mathematics because they also are very precise. Is there any suitable probabilistic interpretation or way of encoding probabilistic interpretations in formal systems that would let techniques for AI developed for them be more broadly applicable?
That's a good question. I don't have any quick or easy answers, ready to mind. I think an interesting question is, when it comes to getting AI to do practical things, do we need to pass through the mathematics? I mean, so for example, you can imagine if you want to build a bridge, one model is, you ask ChatGPT to, design me a bridge and it should carry this weight and so on and hope for the best. The other one is, you ask ChatGPT to give me the mathematical specifications and the proof that it's correct and so on. I think for a lot of problems, we'd at least be more reassured to have not just directions from our AI, but actually the mathematical explanations and reasons and justification. So I think it is, yeah, I think focusing attention on AI for mathematics is, I think it's important for thinking about, AI in general and how to make it useful. I think there's some things that, that maybe AI can do that maybe does not need to pass through mathematics. But I think a lot of things that we want our AI to do for us, having mathematics kind of centrally in the loop is going to be important.
It's interesting that you connected that question to the broader question of, what, doing successful AI for mathematics will let us extrapolate to in broader AI work. So maybe Al-Hussein, you also have questions here. What is the what can you get from getting very good at AI for mathematics? What can this teach AI systems in general?
So I think one of the things that is specific to AI for math is, as I said, symmetries and invariances. So this is something that is quite difficult to incorporate, or like it takes time really to incorporate. So by having more symmetric and having more customizable potentially architectures, I think this can help us a lot. Can help also the machine learning community. As I said, on the interpretability side, I think is also really important. So we are really driven by the performance, but I think what AI for math will help us, the domain of math will help us improve in machine learning, is getting models that are more interpretable. Models, as I said, that would allow us to read into the decisions and that can transmit to the domain expert why it actually took those decisions, rather than just, look, I took those decisions. I can verify that they are correct. Sure, you can verify that they are correct, but why did you actually take those decisions? And can we have a more concise description of the decisions that you have made that is interpretable to a human? I think these are two domains that are, I think will improve the machine learning community.
Thank you. On the slide, there's been a lot of discussion of, following up from our earlier questions about what the right benchmarks for mathematics should be, perhaps not even just for specific problems, but also more generally. Jeremy, I know that you've done some work recently in putting together a benchmark for broad spectrum mathematical reasoning. Do you want to talk about that a little bit?
So I'm not sure what you're referring to. Well, let me say, so on the formal methods side, so as on the machine learning side, in formal methods, also the availability of benchmarks have been a powerful force in driving the field. So for first order theorem provers, they're the TPTP benchmarks, so thousands of problems for theorem provers. SAT solvers, SMT solvers have similar libraries and challenges and competitions. And, in each case, they really do a great job of driving research forward by giving clear metrics and measures of progress. There is the danger that, sometimes systems are then overtuned to the libraries. So you have to be a little bit careful, but it really kind of spurs activity in quite a good way. But one thing I was thinking of while Al-Hussein was talking about this topic was that this is really a marked difference from mathematics. Mathematical research is not, to some extent there are open problems, and we reward mathematicians for solving open problems. But often with a mathematical inquiry, you don't even know what the questions are, or you think you know some of the questions, but new questions arise. And so I think this is another sort of important difference between mathematics and computer science. And again, the way we evaluate mathematical research and progress is really quite different. And I think it's helpful to have domains where the two come together rather than just relying on one or the other.
Maybe I'll get you to say a few words about the work on ProofNet, which is what I was thinking of specifically when I asked you about benchmarks. So I know that this was your work putting together an undergraduate level benchmark. Is this a space that you had thought was missing before?
Yeah. So this work, the work was done. So it was led by Jahangir Azarbayev, who was a talented undergraduate from Yale who visited me last summer and did remarkable work, and Bartosz Piotowski, so a PhD student from Poland who came to visit for a number of months. And yeah, so this was it was exactly for that. It was so the idea was that so one of the things that's been driving research in machine learning for mathematics has been the IMO challenge that Daniel Selsom said. So that's an important one to try to solve IMO problems. But IMO problems are kind of a very specific type of mathematical problem. We thought that what you really want is so another important kind of benchmark is to use textbook exercises to see if we can get machine learning systems to do well on those. And there, that's useful because textbooks, so the machine learning systems have access to all these textbooks. So they have access to the conventional, theorems and proofs. And the exercises are typically given to students. They're kind of things that are built on top of that. So if one might hope that if you train an AI system on conventional textbooks, that they can learn to do the exercises. So yeah, and there are a number of projects like that, trying to sort of gather good benchmark systems of mathematical problems. So yeah, that was just one that we chose to focus on just standard undergraduate textbook problems.
Let me turn the conversation completely. In Jeremy's talk, there was a discussion of what gets rewarded in academia, both on the computer science side and on the math side. And Jeremy made this point that somehow there's a chicken and egg problem with, computer scientists needing mathematician users and mathematicians needing tools that are already good enough to make progress on traditional problems. Al-Hussein, you work in industry. I wondered if you could give us a sense of what the reward mechanism is in industry and how you see the challenges there in terms of getting this kind of work supported.
Yeah, so I can speak for the company I work for. So I don't know about other industries, but so the reward is so I work in the science team in DeepMind, which tries to tackle big challenges in the sciences, in particular in computer science. So what we are really after is high impact problems, very high impact problems in the areas that would be deemed as very high impact by the mathematicians themselves or by the scientists themselves. So yes, that's I think makes one of the makes DeepMind a sort of a unique place where we can gather indeed like different domain experts in the science and engineering expertise and research scientist expertise in machine learning. And I think this is very hard to probably gather in other places. And the goal being really that we would like to publish in top-tier journals and do breakthroughs that would be really considered as breakthroughs by the community, by the mathematicians themselves in the case of math. So yeah, that's how the model of DeepMind works, in particular in the science team. Does that answer your question?
Yes, it does. Thank you. And I think what's interesting there is that it sounds like for you, as for Jeremy's description of academic incentives, it sounds like what we live or die on in the end is progress that traditional mathematicians consider important.
Yes.
Okay, I think we nearly need to wrap it up. Maybe one final question. So you've both, I think, talked a lot about what makes mathematics a special domain in terms of importance. Sort of more broadly, what lessons from math for AI for math can be taken to AI more broadly. But any quick thoughts about what makes it hard? So I know that Al-Hussein, for example, talked about the difficulty of optimizing average performance versus performance on a specific target. Jeremy, do you have any other broad thoughts to add about what makes AI for math a special problem?
So in formal methods, what makes the hard is the heterogeneity. So, we have systems that can solve, propositional logic, with problems with, with millions of symbols, tens of thousands, hundreds of thousands of variables, but the problem is very well posed. Mathematical proofs sometimes can be quite short, but they'll bring together ideas from totally different domains and so on. So it's the heterogeneity of mathematics. I mean, the solution is not size. The complexity is not the complexity. It's just finding just the right ideas. I think we don't know how to do that yet.
Great. So thank you both for a very interesting session. I'll pass on to Petros now for the next session, which is the role of intuition and mathematical practice.
Thank you very much, Heather. Now I have the great pleasure to introduce two distinguished scientists joining us from Europe. Ursula Martin holds the emeritus professorships in the Universities of Oxford and Edinburgh. Her research initially in algebra, logic, and the use of computers to create mathematical proofs broadened to encompass wider social and cultural approaches to understanding the circulation and impact of foundational research in computer science and mathematics. And after Ursula, we will have Stanislas, who is a professor at Collège de France, and he's the director of the INSERM CA Cognitive Neuroimaging Unit at the Neurospin Center in Paris-Saclay. And this is France's Advanced Brain Imaging Center. Stanislas' interests concern the cerebral basis of specifically human cognitive functions such as language, calculation, and conscious reasoning. We are looking forward to an exciting hour. Intuition is something that is for some of us a mystery, and we're looking forward to the next hour, starting with Ursula. Ursula, over to you.
Right, I'm waiting to be told I can share my screen. Right, thank you. Sorry, the screen is full of silly pop-up messages. Right, that's better. So I'm speaking to you from Oxford, and that's the view from the window, where it is the middle of the afternoon. It's exceptionally hot, and it's the last week of term. So there are a lot of happy, noisy people out there. So what I'm going to be talking about is a bit complementary to a lot of the amazing stuff we've heard about already. I'm going to introduce you to the world of ethnographers and social scientists who look at mathematicians and think about what mathematicians are doing. I'm not going to say much about AI, except to think about what lessons this work might give us for trying to address the major challenges that we've been talking about in this meeting. So, the world of mathematics, the map of mathematics. There's a vast sea of potential mathematical knowledge covering every area from foundations to pure mathematics to applied mathematics to mathematical modeling. And when we talk about mathematics, we're talking about that vast sea of possible theorems, possible conjectures. We're talking about actual mathematical knowledge, which has been accredited in some way, typically by the traditional process of publishing research papers, or in a company by the whatever internal means, as we've just been hearing about, the company would be using to accredit it. And then around that, we've got all the infrastructures that make that mathematics happen. We've got the people themselves, the workforce, as it was called in the introduction to this meeting. We've got the institutions, the employers, the publishers, even the funding bodies who've brought us all here. And when you think about it, it's rather amazing that mathematical publications haven't changed much since, well, I put there because I'm a Brit and I'm based in Britain. Here, of course, is a picture of the philosophical transactions of the Royal Society. Started publishing papers, mathematical papers included in the same sort of model as we have today, way back in the middle of the 17th century. And what this slide is showing you is the vast growth in mathematical publications, even over the past, 96 to 2022, 25 years. So in the UK, that's the orange line, where it looks as if we're holding pretty steady. Actually, we've almost doubled, but but if you look at the vast growth in mathematical papers in India and China, there are huge mathematical communities that are not often represented in the kinds of conversations we're having in this meeting, which tend to be normally dominated by the North American and the European axis. But as I say, we've got this big ecosystem that contributes to these mathematical publications, not just the researchers originally produced the research, but the eventual deployment of the publications. I mean, we all know these jokes about mathematical papers that are only read by two people, the author, the author's mum, and the referee. But of course, if a mathematical paper is effective, is useful, it's part of a broader conversation, it's going to be taken up by other researchers, it's going to be taken up by educators in some way, either immediately or feeding into textbook use, into education. It's going to be taken up by users in some way, this concept of impact that we've just heard mentioned. But what I'm going to talk about is, where does the math come from? Well, in 10 minutes, I'm only going to give something very brief and cursory and perhaps a little bit glib, but let's start here with a classical example of some math. Here is, I'm trying to be American and say math, everybody, please notice. Also, it's shorter on the slides. Here's a kind of quintessential example. Andrew Wiles' proof of Fermat's theorem. Here's a typical page taken from the middle of the paper. There's a picture of Andrew himself, and just to set a little bit of context, a page from where Fermat first wrote about it. Now, if you wanted to understand the paper, well, you might try and read it, but that would be a pretty optimistic ask for more than a very small and specialized group of mathematicians with the right kind of background. And you can see when you look at it, is the pointer working? Why is it difficult to read this? Well, because you're using weasel words like analogous. An analogous definition, you have to be rather steeped in the club to know what analogous means in that context. There are all kinds of techniques being talked about. Extensions are computed, blah, blah, blah. Something's unique. Just passing on, we've got something that's entirely analogous. We've probably got a similarly in there. Mathematicians will know that's a page talking about some kind of cohomology. Proofs in that kind of cohomology typically involve what's called diagram chasing, or checking lots and lots of details. And so when Andrew's saying calculation, that's what he means. He doesn't actually put the calculations in the paper. Those are exactly the kind of details that a theorem prover could get a grip on. Maybe theorem provers tackle this sort of thing already, I don't know. But if you wanted to know how Andrew came up with this, obviously it didn't spring fully formed from his mind like that. You'd have to dig around in the books of yellow pages. You can just see in the back of the picture. Or, of course, because Fermat Andrew's result was very significant, he then talked about it quite a bit in public. The first quote is from a TV interview where he's talking about creativity. And the TV interview, you can see the interview, when you watch it, the interviewer wants to get the cliche of Andrew talking about the moment of inspiration, the moment of genius. Sometimes I realized nothing had ever been done before was any use at all. I had to just find something completely new. It's a mystery where that comes from. And if you've seen the movie, there's a sort of a pause. I think the filmmaker is desperate for a tear to fall from his eye. I don't think it does. And I just heard in the talk yesterday about Claire Voisin's article where she makes similar kinds of points. But when you listen to Andrew's interview, the filmmaker wants you to think about the genius, the creativity. Actually, what he's talking about in great detail is what comes before that. The slog, as I call it. I started trying to find patterns. I did calculations, explain a little piece of mathematics. I tried to fit in with some previous broad conceptual understanding of some part of mathematics or clarify things. Sometimes that would involve looking at references to see how it was done. Sometimes it was a question of modifying bits, doing a little bit of extra calculation. So there are all sorts of things going on behind the scenes that don't make it into the final paper. And in the broader agenda, computation had a huge role. The Birch-Swinnerton-Dyer conjectures, the truth of the Birch-Swinnerton-Dyer conjectures, or the apparent truth, which was verified by vast quantities of computation back in the, not quite hand-cranked, but getting that way in the 1960s and 70s, it was the truth of the Birch-Swinnerton-Dyer conjectures that gave Andrew Wiles some confidence to try the approach that he was using. And Andrew goes on to talk about a journey through a dark, unexplored mansion, a bit like an adventure game. After 6 months, you find a light switch, then you have a breakthrough, and so on. But all of these, all of the breakthroughs are the culmination of, and couldn't exist without, the many months of stumbling around in the dark that precede them. Perhaps we're going to hear more about that kind of thing in the next talk. The point is that when you're stumbling around in the dark, trying all these different ideas, your brain is making all kinds of connections, building a big, broad understanding of what's going on. So your brain, Andrew Wiles' brain, before, and that's what primes you to make the thing that's the discovery. Here's Mariam Markizani, the first woman and the first Iranian to win a Fields Medal. She was filmed, and she made notes on these actually great long rolls of wallpaper of exactly of how her thought processes were going, and you see the kinds of things that she was doing, playing with different ideas. Ethnographers, and if you haven't read it, I can recommend a book by Donald Mackenzie, a social scientist at Edinburgh, Mechanizing Proof. It's quite old now, but he looked at us. And some of his observations are actually extremely perceptive. You read it and you think, oh, yes, that's right. But as somebody on the inside, I've never thought of that. With a student, Michael Barani, he talks about what an enormous amount of work goes into decoding, translating, and transmaterializing official texts without which advanced mathematics couldn't proceed. The great amount of work, if you're reading in detail a paper like Andrew Wiles, it's a great amount of work that goes into understanding what it's saying, tweaking it a little bit for your own, to match the context in which you're trying to apply it. And one of the challenges can be, and this is the sort of thing that keeps historians of mathematics in business and suggests why we do need theorem provers, is what happens if nobody can remember what Andrew Wiles meant by analogously or similarly? If you have to try and reconstruct it, this kind of shorthand among friends it's not necessarily wrong, it's just can be extremely hard to follow 10, 20, 100 years later. I think this picture was taken at the Newton Institute. I think some of the speakers here are in this picture. And if anyone can remember whose hand it is on the right, of course, the person in the middle is Vladimir Fawzi, is no longer with us, another Fields medalist who was mentioned yesterday, who did a huge amount to get mathematicians thinking about computer theorem proving. But the point of putting up this picture is to stress the importance of collaboration, of talking to other mathematicians in moving the mathematical enterprise forward. And another social scientist, Lorenzo Lane, spent quite some time hanging out with these guys. He articulates more precisely what's going on because when people are collaborating, things that would normally only happen in one head, so you can't really capture them. If people are talking or talking on a whiteboard, then it's easier for somebody watching them to figure out what's going on. And he talks about the work of pulling apart ideas, putting them back together, a bit like a jigsaw puzzle of ideas. The co-creation, working together to create languages, concepts, and conjectures. The sharing of feedback, insight, informal knowledge, building rapport and trust, socializing ideas. Now, that's actually a very important part of the mathematical process, because your paper needs to speak, mathematics needs to speak to some kind of mathematical community. People can say, well, actually, this is maybe this. Should you be socializing your ideas with people in the pub? Should you be socializing your ideas with the potential referee of your paper? Well, that's how it happens. The initial ideas of some big piece of mathematics will be circulated among the community before the actual paper drops. Anyone who's following the conjecture around the ABC conjecture, this is a piece of this is a conjecture proved by some Japanese. What? Sorry, the co-host has asked me to start my video. I have no idea what that means, because I thought I'd started my video.
We can see your slides, but not your face.
Oh, you can see you can't see my face. Oh, I see. Sorry, I thought for some awful minute you've been listening to me for 10 minutes without. Sorry, where do I start my video? Can I just go on with the talk? I don't know where my video is gone. Oh, start video. Okay, right. Sorry, I don't know where my video is. I've been waving my arms about a lot, folks, and you missed it. Right. So we're talking about collaboration, but part of the controversy about the ABC conjecture, the paper dropped, and it was very in Japan, and papers have been published, and there was a lot of controversy about this, and part of the controversy centered around people, Western mathematicians, saying to the mathematicians who'd done work, well, you're expecting us just to digest this huge new theory that's dropped from nowhere, and you haven't done any of the work. We would have liked to help you explain some of the ideas in simple terms, and philosophers have helped unpick this. It's a very interesting debate, what's going on. But of course, while people are in the pub and sharing these conversations, they're also developing and reinforcing a shared culture of what mathematics is. They're inducting new students into the shared culture, shared memories, shared myths, ideas of what the philosophers call mathematical virtue, idea of what's important, what's beautiful, who's a hero, who's a genius. And these, these are not, there's not some, well, I don't think there is some idea of, unique idea out there, Platonic idea of what's mathematically important. These are ideas grown and shaped by communities, and this kind of collaboration is what grows and shares them. And I gave a talk about this before, and Barbara Fantecchi was watching on Twitter and reminded us all that I hope you're aware how I asserted over beer already shows how you and whoever was beer drinking with you already start from a position of privilege. Well, what I'm going to talk about now for just a few minutes is a mathematical experiment, an experiment in doing things differently, not an experiment in collaboration, and not the traditional write a paper and then have it refereed model. This was a polymath collaboration put together by Tim Gowes and Terry Tao. Gosh, it's 15 years ago now. The idea was that a group of people would collaborate together to solve mathematical problems on a blog. And here's some typical piece of the conversation. Somebody called Pace has gone away and done a calculation. Terry has checked it. Terry has checked it in Maple and so on. Here's a piece of a conversation where somebody's asserting something. Somebody else is saying, no, I don't think that's right. Here's a counterexample. And first Pace is saying, yeah, you're right. That's a counterexample. Forget what I said. And so this is capturing in even more detail, if you like, mathematical conversations where people collaborate to put together a proof. One of the reasons it worked is that leading mathematicians took great care to set ground rules. Be polite and constructive, make your comments easy to understand, and so on. Be nice, basically. It's okay for a thought to be tentative, incomplete, or incorrect, but don't be nasty to other people when they make a mistake. And a lot of work, and we can all think of online communities that are not like that at all, scare people away and are not especially happy places. The people running this were putting a great deal of effort into trying to make it a constructive community. And papers were produced. Here's one from 2019. A paper was produced under collaborative authorship, DHJ Polymath, because the first problem they attacked was the density Hale-Stewart problem, DHJ, density Hale-Stewart. Now, the community themselves also did some very thoughtful analysis of this project, because it's fair to say that while it was an exciting idea, it only worked for certain kinds of problems. There haven't been that many polymath papers. And it was very interesting to see that analysis led by a paper led by Terry Tao. What are the challenges of all this? Well, first of all, it's a very hard job. Initially, they thought it would just kind of self-organize, but it never self-organized. There had to be a leader who, in this case, was typically was Terry Tao, and it was a very demanding job. The leader had to keep track of the mathematical conversation and have the kind of people skills to just guide things, nurture things, choreograph things, steer the conversation in different directions if it looked like people going down a dead end. It all went very fast, and literally not everybody had the time. Terry himself didn't have the time to sit in front of the screen and watch all this happening. People need to eat and sleep and play with their kids. One of the things they wanted to do was to allow, well, anybody could see this, but also to encourage other people to join the conversation who wouldn't normally, so to speak, be in the pub. But that had the downside that you had to be rather brave to join the conversation, because if you did make a mistake, even among this kindly supportive community, a lot of people would see it. And so that then led to the question of who actually was in the room, who was part of it. Well, there were, people were, when you talk to people about why they did or didn't take part, well, exactly this thing that has just been mentioned in the previous talks came up, credit and attribution. If you're up for tenure, nobody's going to think very highly of, well, yeah, I did contribute to this paper by DHJ Polymath. And actually, if you go and dig around on Michael Nielsen's blog, you can find my name listed. People wanted to spend their math time on things that would bring them personal credit. And so that was a disincentive alongside making mistakes in public. And so that left one wondering, well, who was in the room? Was it pretty much the same sort of people as before? But it was I'll come back to the polymath experiments in a moment, in the context of talking about, can we do mathematics differently in the age of AI? Do we need to do that? But one of the things we did, mini polymath was a little polymath that they did along the way. You see, as we pointed out, this isn't Tim Gower's musing about, well, I tried a bit of an idea. This is actually people writing down what they did. And so one can go away and analyze it and say, well, in this group of people thinking about doing a particular proof, what did they spend their time doing? Well, this was the hand analysis by my colleague Alison Pease and myself of a couple of these small polymath examples. Well, of course, what was interesting was, of all these steps, only 14% of them ended up being actual proof steps in the final proof. A great deal of the steps were thinking about concepts, thinking about conjectures. In other words, exactly that kind of playing around with different kinds of ideas that Gal was talking about, that Mazagani was talking about.
Ursula, maybe a 3-minute warning.
Yes, I'm nearly there. Thank you. I'm nearly there. But when you look at this, and that's why I put this slide in, if you drill down into these things individually, of course, these are exactly the kinds of things that people are thinking about and have been thinking about a long time for using AI techniques for. I mean, you don't have to be part of the current community. You can dig back in old papers of things like the CADE conference, researchers like Alan Bundy. How do you automate concept formation? How do you automate example search? Can you build a big database of examples in such a way that it's useful, and so on? And so the things that people are doing match very much these ideas that are being played with.
Ursula, I was wondering if you could summarize so that we can...
Look, Petros, you haven't interrupted. Nobody, other speakers have not been interrupted or interrupting me. I'm on my last slide. Thank you.
Thank you.
Now, this is my last slide. And I've taken for it the slogan from that we heard in one of the talks deliberately. What should the growth of AI do for us? It should encourage us to live deliberately, to think about, to plan about this world where AI might deliver huge mathematical abundance, formally proved, well evidenced, but not formally proved, or more speculative, which is another way of saying just plain wrong. Now, if you look at the role that you might say in this world, you need traditional mathematical papers, but you need to stop and think about what traditional papers do for us. They present an organized new mathematical knowledge. The mathematical knowledge is accredited by proofs or by other means. Traditional papers can certainly accommodate computation or chunks of formal proof. They're refereed, they're published, they give us notions of credit, attribution, and accountability. And they sit inside these user ecosystems of scholars and research users who guide the ideas of importance and of impact. And all of that is very important. If you just toss it out and say, well, let's just have a fire hose of AI-generated mathematics, you could set Maple to give you a new polynomial every morning and solutions to it, but it wouldn't really help mathematics. We still need to keep all these ways of thinking about mathematics. And so this is my main message. Making math, thank you, Petros, I'm now summarizing, is not just about making proofs, it's about understanding the broader context, and which will better allow stakeholders, all the different stakeholders, to collaborate on making AI ++ math, or indeed mathematical barn raising, which we heard about in the previous talk. Thank you. I'm done.
Thank you, Ursula. I would like to turn it over to Stanislas, and it would be great if we have some minutes in the end. There's many great questions here in the chat. Stanislas, over to you.
Hello, everyone. Hello, Petros. Hello, Ursula. I'm very happy to be with you. Let me start sharing my screen. I think, yeah. Just take a second. I hope you can see it now. There we go. So I come from a very different perspective as the previous speakers. I come from the perspective of psychology and cognitive neuroscience. And nevertheless, I love mathematics. I love mathematicians. I am a mathematician myself. And what I'm trying to do in my work is to understand the sort of brain architecture that allows the mathematician's brain to capture facts about mathematics in a way that other species cannot. But maybe this baby here, as you will see, is able already to have mathematical intuitions. Of course, what I want to discuss today falls into a broader question, which is how well does current AI, in particular artificial neural networks, mimic human cognition and learning at all? This is something that I discussed in this recent book, How We Learn. I think that we have made enormous progress. And as models of the brain, current artificial neural networks are very good at helping us explain how small synaptic changes between neurons can lead to very sophisticated learning. And they have been very good at capturing the early stages of vision, in particular reading, but also language processing, as we see in the large language models recently. But it's not fully satisfactory, and there are many, many ways, in particular in mathematics, in which AI is not quite there yet, and the human brain keeps the upper hand. For instance, I will show you examples where the brain learns from a very small number of examples, sometimes a single trial, using very efficient Bayesian-style reasoning, probabilistic reasoning. And we consider that the young child, even the baby, is a scientist in ways that AI is not mimicked yet. I want especially to discuss today the fact that the brain learns through a combination of approximate intuitions, but also very precise language-like symbolic expressions that do not seem to be very well captured by artificial neural networks, at least yet. And therefore, we discover in mathematics compact, abstract, symbolic representations of knowledge, even as young children, that are extremely efficient. And one aspect also that strikes me, but I guess I won't have time to talk about that today, is that the human brain remains much better in its achievement of explicit representations, therefore being able to share information with others and learn from others and with others, which is obviously very important for the mathematical community. But for lack of time, I will concentrate on the middle statements here, approximate intuitions combined with language-like symbolic expressions. So first of all, I'd like to remind you that there is enormous mathematical abstract information already in the mind of a young baby and even a neonate child. And they understand about numbers and about probabilities in ways that are not present in untrained artificial networks. So there's something that is given to us by evolution here about intuition. I want to show you a few examples. If you look at this movie, which has been shown to young babies, you see 5 objects hiding behind the screen. You see another 5 objects going in, and then when the screen drops and you see only 5 left there, and you should be like this. You should be looking at this, staring in disbelief, because this is 5 + 5 = 5, which is impossible. Babies know about this, and at a few months of age, they already stare at the screen when it presents a violation of number or arithmetic. It's not that they know exactly 5 + 1 = 10, but they know it cannot be 5. They know approximation, can approximate. And if I give you another example from the work of Teglas, Bonatti, and others, here you see 3 blue objects and 1 yellow moving around randomly. And we get used to 3 blue and 1 yellow. And then they hide. And you see 1 yellow dropping. And again, you should be surprised because there was only 1 chance out of 4 for the yellow to come out. And babies show surprise in direct proportion to probability. And many experiments suggest that they compute Bayesian probability. They really take into account the prior and the possibility of computing the posterior. So they have a lot of knowledge. And this is also the case, also it's much less demonstrated in the domain of space and geometry. And I use these examples here to show how deeply ingrained in human cultures is the capacity to do geometry. When you see in the Lascaux cave, not only these drawings of animals, which are so famous, but also this rectangle or this line of dots, you know humans were there. Only humans make geometrical drawings such as these, and they can be very old. This is at least 70,000 years old, this piece of Hawker's parallel lines. Zigzags are all over the place. We have abstractions that other animals do not seem to achieve. And I want to give you examples of the experiments we do in the lab. We try to measure the strengths of these abstractions, even in very young children. So for instance, if you're a young child coming to the lab and you are maybe in kindergarten, you might see this display where there is 8 locations, and we show you a fish moving through these locations. And we're going to ask you to guess where it's going. I hope you could see this, and I stop in the middle, and I think you all can guess that's going to go there, and there, and there. You see how quick this is for learning. This is not even one trial learning, this is 1/2 trial learning. You already know what's coming to go next because it's a zigzag and you perceive the symmetry around this axis and the fact that the animal was going back and forth. We've studied this extensively in the lab, and we found that even though it looks simple, in order to account for all of the possible sequences and which one do you find simple and which one you find complex, we have to assume that young children, adults, even without education, have a sort of intuition which takes the form of a language of thought. They have primitives of rotation, they have primitives of symmetry, they have a capacity to combine these into a formula like this is the zigzag, repeat 4 times, that you repeat twice a symmetry operation, and you'll get the zigzag. So people have an abstract representation of these sort of sequences. We have been able to track it in the brain. First of all, behaviorally, what you can see here is that what we call Kolmogorov complexity, or essentially minimal description length, how long is the formula, the program to express the sequence that you've seen is a determinant of how well you can anticipate or remember these sequences. Sorry about that. So essentially, you could not remember an 8-item sequence if it was not regular. If it's very irregular, you have no capacity to remember it. You can remember it only if you can compress it in your mind using this sort of language of mathematics, or sort of proto-language of mathematics, which exists even before education. We track it in fMRI. We see that there is a whole network of areas that are dorsal in both hemispheres of the brain, by the way, both the left and the right, for this sort of spatial language. And they have this capacity of increasing all the way up to the most complex but understandable sequences, and then they collapse for the sequences that are too hard to understand. We can also track this for other methods of brain imaging and show really that what we postulate in this language of thought is present in the subject's brain. One key postulate is that even though it's just a sequence of 8 items, if it is graspable, people will group it. They will group it in groups of 2, for instance, for the zigzag. They might group it in groups of 4 if it's another sequence, like one arc followed by another arc, or maybe one square followed by another square, which people understand readily. And we could show from the brain signals in magnetoencephalography that there is a trace of that in the subject's brain. They have a power spectrum which shows peaks at the proper grouping period here, suggesting that they really encode these as loops within loops within loops. They are the language of thought, a sort of proto-mathematics, even without education. And brain decoding has become quite advanced, thanks in part to AI advances. We can decode which is the number that is in this for loop in the subject's mind, even though they are not telling us anything. Just by looking at the brain waves, we can tell about where they are in this mental program. There is even much simpler, and I want to appeal to another kind of intuition, the intuition of shape. I just again put you in the same exact shoes as our subjects in this task, which also include young children. Where is the outlier? I suppose you can immediately spot that there's an outlier here because everything is a square and this one is not a square. Where is the outlier here? It's a little bit more difficult, right? But everything is a parallelogram and this is not a parallelogram. Where is the outlier here? Much, much more difficult. It still is this one. The shapes are identical except for this one. And we always move this corner, but it's more difficult. So what we found here, to cut a long story short, I don't have time to explain everything, but we found that subjects are extraordinarily sensitive, even without education. We tested all sorts of subjects, including preschoolers and also people from Namibia without easy access to education. We found that everybody behaves the same. It's a sort of human regularity. Everybody finds rectangles and squares, simple shapes, as easier to detect the outlier. But everyone has a lot of trouble, and I'm speaking about close to 50% errors here with the shapes that are not regular. And we think there is something quite particular here because it's not the case at all in a non-human subject. We were able to test baboons in this task. It's easy enough for a baboon to pick the outlier, and they can do it and they progress through the task. But as you can see, they don't care at all, unlike us, about the mathematical regularity. So I'm talking here about a system of intuitions of number, of shape, which has the same foundation in evolution, but in humans is a mental construction through a language of thought, an internal language, which reaches more abstract levels, and in particular the concept of a square or the concept of a rectangle, I would claim, are not accessible to non-human primates, but are accessible to all humans because we have this sort of combinatorial ability. We can formulate in this language of thought that this is a shape with 4 sides, 4 equal angles, 4 equal sides. One very interesting thing in this experiment is that the
did we lose Stanislas?
I think it might take a minute to come back on.
Stanislas, I think you were interrupted for a few seconds. If you could
I'm sorry.
go back just maybe 1 slide.
Yeah, I'm very sorry. I don't know what happened here. I'm glad at least that this was perceived. Can you see this slide now?
It's yes, please go ahead.
Okay, so I just repeat what I said, hoping that it's not too redundant. So what you can see here is that all the baboons behave in a similar manner in this regression plot. They have similar behavior. So how can we explain that? We were able to explain it by appealing to a classical model of vision, convolutional neural network. All of the baboons are well explained by assuming that they just see these shapes and treat it as they would treat an object or a face through this ventral visual pathway. But that these sort of regressors do not explain what humans do. And in order to explain what humans do, we have to assume that they have a sort of mental logic, that they have symbolic properties like parallels, right angles, equal sides. And if you just list these properties and see how they differ, you can spot the outlier and mimic what humans do. And very interestingly, if you're not educated or if you're a young child, you have regressors for both models. So we think that the human brain contains both a sort of intuitive processing of shapes like a face, but also a discrete symbolic model that is not present in other animals. So I'm close to my conclusion now, but I just want you to show you a few examples of what I think is a trace of a rather deep failure of current AI systems to match our mathematical intuitions. So I will give you just examples, but I think they reflect a deep reality. One example is the processing of geometrical shapes. It's not just squares and rectangles. It's really a deep critique, I think, of the ability of networks to understand what is a geometrical shape. So one example is if you look at this picture here, I think you all recognize that this is eggs in the fridge door, but for a neural network, it was depicted as ping pong balls. And that's a little bit funny. We all know these are not ping pong balls because they do not have the right spherical shape, but the networks are not attuned to the precise geometrical properties that make a sphere, or that make a circle, or that make a square. And if I go back for a second, this slide is actually a pretty strong critique of current artificial neural networks, because we could not find a single neural network that was able to match what humans do. Even if we took more advanced networks, AlexNet, autoencoders, and so on, for the moment at least, we have not found one. I'm not saying it's impossible, but I'm saying something is missing in the current AI approach to capture this sort of mixture of intuition and symbolic representation that humans use. So a few other examples. I think that François Charton may have talked about this. There is wonderful examples of mathematics being done by AI, for instance, for integration, and yet there are wonderful failures as well. I'm working on the comprehension of fraction, and here's my recent conversation with ChatGPT-3. What is larger, 2/4 or 1/2? The answer, 1/2 is larger than 2/4. 2/4 can be written as 2/4, which is equal to 1/2, therefore 1/2 is equal to 2/4. Didn't you just contradict yourself? Oh, I apologize, I made a mistake in my previous answer. 2/4 is smaller than 1/2. Are you sure? Yes, I'm sure 2/4 is equal to 1/2. Since 1/2 is larger than 2/4, it follows that 1/2 is larger than 2/4. My goodness, this network is completely confused. And I think if you dig a little into the surface of the language these networks propose, you find that these language models really have very, very little in the way of the geometrical and number line properties that characterize our understanding, our intuitions of mathematics. I can give you other examples. We are all very impressed by the ability of DALL-E, for instance, to generate pictures such as this one, Darth Vader in a 19th century dress. But if you ask it, imagine a green triangle to the left of a blue circle, this is what you get. You don't get the sort of logical, structured, spatial representation, geometrical representation that humans will generate when they are 3 or 4. So we are missing big on the intuition which is present in very young children. Current AI often has a problem with represented nested logical and geometrical structures. Again, I'm not saying it's impossible, and each time you make a statement like this, somebody will point you to a paper from last week which has solved the problem, so it's moving very fast. But we have to think deeper, and I'd like to point to one thing that we discovered in cognitive neuroscience, which is that language and mathematics are actually processed by very different brain networks. Spoken language activates the area in green here for the general semantics of natural language, such as understanding the sentence, the Paris metro was built before the Istanbul one. But mathematics calls upon the network in blue, which we systematically find whenever you think about very high-level mathematics, but also simple arithmetic or algebra, or just very simple statements. The sine function is periodical. So to conclude, I think we have in AI massive progress in modeling language and having large language models that are able to predict quite well what happens in the language network. It's getting better and better. So we're not quite there yet, but it's getting better and better. I think modeling the dorsal mass responsive network will require the same sort of effort, which we haven't seen yet, which is really to try to capture better the kinds of intuitions that are already present in young babies. Innate constraints for space, objects, sets, probabilities, and perhaps also a built-in learning bias in order to easily detect repeated symmetrical or recursive structures. I think the human mind has developed a network, which is in blue here, for attending to this sort of symmetrical structures that we call mathematics. And it's a sort of symbolic language, but it's not the usual natural language that we use to speak to each other. It's an internal language made of symbols that we are only starting to decipher with our methods. So with that, I think I would like to close. I don't want to give a pessimistic message. I think we're making enormous progress, on the contrary, but something different will be required in order to fully capture what is happening in this mass responsive network as opposed to the classical language networks of the brain. Thank you very much.
Thank you very much, Stanislas, and thanks again, Ursula. There have been a few interesting questions here on the chat. Maybe I'll try to combine two of those. There is obviously the capability or there is work on automatically verifying proofs. And of course, some of these proofs have already been discovered. Is it possible to have to prove new theorems? Is there anything that can tell us that AI has the capability to do something in that direction, besides automating a process that we already know how it works, kind of, or we see it.
The real question I would like to ask is whether AI can not only discover proofs, which has been achieved, I think, and through intensive search in particular, but whether AI could imagine a new meaningful mathematical fact. A new shape, for instance. Could AI by itself discover the 5 Platonic solids? I'm not sure whether that could be the case, but this is the sort of imagination or intuition that I think is lacking at the moment. Churning through symbols, yes, that I think is being done at the moment.
Would you count protein folding as meeting your criterion?
Yeah, it's getting closer. It's
I
interesting.
mean, that's
It's a very restricted problem.
Sorry, I can't start my video for some reason, but yeah, I mean, there are. I think there are. I think the thing is, there are so many. You know, once you start unpicking language, once you start saying, you know, what is meaningful? Well, you know, meaningful is in the eye of the beholder. Meaningful is, but you can. There are examples. I mean, there have been examples of things that are. Well, you could say they were just brute force search, but they were much more sophisticated than brute force search, because they had to be brute force search with a lot of guidance, with a lot of extra stuff built on top of it. Otherwise, they would never have succeeded. But finding elaborate combinatorial objects, for example, finding particular kinds of projected planes. I mean, there are certain. And of course, you can then say, well, that's not really mathematically interesting, but
So Ursula, could it be that AI produces results or does things that we as humans don't have the capability or the intuition or what have you to explain or to understand? So it's not the fault of AI, but it's maybe the fault of our particular brain?
I'm sure it is, and I think somebody else in the room might come up with some good examples. But you know, we've already had. I mean, the idea of AI making conjectures, the idea of AI being guided and making conjectures in knot theory, which the mathematicians themselves had not made, that kind of thing, and then. It's not too hard a step to go from making conjectures to then, I mean, so it's not too hard a step to imagine from making conjectures to then proving the conjectures. Now, of course, you can also come up with boring conjectures, which the AI will then prove. You know, is there a polynomial with some kind of weird properties? I don't know, but some kind of search, some kind of piece of AI will find that. If you want something where the mathematical community or the general public is going to go, wow, then you've got to prime the mathematical community very nicely to go, wow, I think.
There is an existing paper. There are several existing papers. One is by François Charton on integration, and another is on the Ramanujan machine. And both of them are machines, neural networks that produce expressions that are well structured and that are often true, but not always. And some of them are very beautiful and compact, and they come without any proof. So that's why I think the term the Ramanujan machine is actually quite appropriate. It's almost like out of the blue, here comes this beautiful expression, which happens to be true in 80% of the time, but there is this 20% where it's just false and sometimes blatantly false. I think this is where we are, and it's a sort of very interesting separation between, on the one hand, very powerful exact symbolic systems that go beyond what humans can do in exact symbolic calculation. And then on the other hand, quite intuitive systems, but that are wrong 20% of the time, let's say, roughly, and no bridge between them. And what's very impressive about the human brain is how it bridges. And the same mathematician, in 1 second, will use intuition, and then we'll be able to formalize it. That's what we cannot put in machine learning.
So there is a question actually that is very related, I feel, to what you're discussing now. Stanislav Talia-Renger says, does the math network overlap at all with networks for other tasks that we may not view as math? So for example, writing proofs feels to Talia like navigating through space, and she's always wondering if there is a neurological basis for this. I don't know if you have the same experience, but
we haven't studied so many tasks, but yeah, there is a lot of links between math and space, for sure. It's huge. Even when you think about a single number, you're already activating your sense of space automatically. And you cannot help but think of numbers as a sort of line. And everybody does that. Even people without education, study people in the Amazon, they already think of numbers as a sort of line. So there is a very deep link between this mass responsive network and the sense of space. And you could almost define mathematics as the integration of number and space and logic together in exquisite tapestry of formulas. I think that sort of captures what we do.
I thought that I had maybe, it'd be a little bit convoluted. Picasso said that good artists copy, the great artists steal. So perhaps you can consider ChatGPT or AI as the perfect thief of everything humanity has put together in a language or as a thought or as an idea. So if we follow the Picasso conjecture, if I may, can we think that AI is a great artist, and indeed we are expecting to see amazing things coming out of it? Can we extrapolate that far, or you see limitations?
I'm very impressed by I'm very impressed by the pace of progress, but there is a sort of implicit assumption about the format of coding by vectors, which works to some extent for encoding the meaning of words. But it's not exactly what we call meaning in the human brain. And it comes very obvious when we think about the meaning of a square. We have a very precise logical definition, which is not captured by an approximate vector, which is more or less close to another. So capturing the meaning of a word in everyday language is sort of okay. And still, there are still many problems just in the language domain. But capturing a mathematical concept doesn't work very well with this vector representations.
How about neuromorphic? How about these neuromorphic machines or quantum computers? There's all sorts of cell computing.
It doesn't change anything, I think. It still is the same format, it's just a different machine running it. Quantum computing, but the brain is not a quantum computer for all we know. It's a hot machine and doesn't seem to be making use of quantum computing at all.
But going back to your point about Picasso, I mean, another point with text is that actually, so to speak, the AI is training us. You know, so much of the text that we read from, you know, somebody, was it you said you were in the middle of writing a grant proposal? Now, I'm sure ChatGPT, there are pages of boilerplate in that grant proposal that ChatGPT could write for you. Well, write for me in my grant proposals anyway. There are all kinds of texts that we engage with that are rather boring, and we've been sort of trained to write them in this rather boring way. So much of what we read on the screen from news and so on has already been mediated by this kind of thing. And it's as though the AI in some sense is training us to expect text in particular forms, you know, just like the children's books we read when we were kids is training us to read things in different, and so I think it might, one of the questions on the Slido was about languages other than English. You know, we take it for granted in this kind of form that English is the preeminent language of math. What are people doing with other languages? Other languages where people's use of the language is being less conditioned by things that they read that are already being tuned by AI, tuned by algorithms. I think those are the sorts of things we look at.
On this matter, I mean, one thing that I was impressed with, I show you this failure of DALL-E to do a green square left of a red circle or something like that. But immediately my student pointed out that you could ask ChatGPT-3, please write a program in Python to draw a green square left of a red circle, and then it will work, and it does that. So the ability to convert between one language and another is actually very impressive in these systems. And maybe that's part of the solution. In our brain, we quickly convert between the words of language and the words of mathematics, the concepts of mathematics. And we take advantage of representations of space, and then we go back to the symbols, and we go back and forth in all sorts of directions. If we could have a system that begins to mimic that, and I think we see this now in these large language models, they have 1,000 languages at their disposal, they have computer languages as well. It's getting very impressive and closer to what we do.
So as mathematicians, maybe Ursula, I'll ask Ursula, do you think that mathematical intuition is something that we can program into a computer after all, or maybe not now, but in the future? Is it von Neumann said that if you describe something, then he can compute it. Is that?
Well, I think I suspect one will just keep redefining intuition. I mean, I find it's not necessarily a thing I like to talk about in general terms. I mean, one can, it's a phenomenon, you know, you can see something and one person's intuition is somebody else's not intuition at all. You know, your intuition that there's somebody outside on the doorstep is somebody else's intuition that they actually heard the person, you know. I mean, it's such a slippery term. I mean, I'm sure you can get computers to surprise you. I mean, Ada Lovelace thought that, Alan Turing thought that. You can get computers to surprise you, but whether you want to call that intuition is a different question.
Stanislas, any thoughts on that?
I have no doubt that in principle, the brain is a sort of information processing machine, and what we call intuition is information processing, and it should be mimicked in a machine one day or another. And I also think we're quite close, but I pointed to you cases of intuitions that occur to us before we learn anything, basically in the neonate. So there is a lot of architecture in the brain that one might wonder whether you need to put such a similar architecture in machines or not. For me, it's a very interesting question whether machines will have to be close to the human brain, or whether in fact we'll find this huge space of other machines that go way beyond what the brain can do, have a much more free architecture. And I suspect that will be the case, much like a Boeing airplane is very, very different from the way birds fly, right? I suspect there will be all sorts of intelligences that are freer from the way we evolved, and that will have actually perhaps better intuitions than we do. I just wanted to say we're not quite there yet.
So how should we go about discovering the airplanes? I like this example very much. So how can we go thinking about things that we cannot think about at this moment?
Well, I think if you talk to Yann Lequin or to people like him, they like to have machines that know very little at the start. They almost make it a point, like the AlphaGo machine. They make a point, alpha 0. They like to start from 0 precisely because they think that the machine may discover other solutions than the one we have. And I think that's an interesting endeavor, even though it's not really matching what we know about what infants do and so on. So it may not be a good model of cognition or the human brain, but it may be a new avenue to other kinds of intelligences. And I'm very interested in that.
So there is maybe I'll close with this question. There is a question by Shimon, says, is it possible that AI will prove mathematics without all the reasoning process that humans do, as it happens with writing poems and editing pictures? I'm not sure it's one-to-one between poetry and proving mathematics, but I wonder if you have some last thoughts about this question, or maybe anything else you would like to share so we can close.
I very much doubt that AI will do this without some kind of visual representation, some kind of mental buffer for space and shape. That I think is deeply missing. If you can ask AI, for instance, picture a circle and a line, and how many intersections can there be between the line and the circle on a plane? And it's very easy for humans, and it's very hard for AI at the moment. It's missing the kind of spatial intuition that we have. That I think is really something that people should worry a bit more. Until we have that, we have like text producing machines that are really not like mathematicians.
Maybe a last thought from Ursula, and then we close.
Well, I think that there is such a sea of mathematics out there already. And you can sort of imagine generating more stuff from this sea. You can imagine more mathematics coming from what we know already and sort of bypassing what Stan just said. But I agree with Stan. And some, of course, mathematicians differ, but sometimes one knows mathematical individuals and their ability to visualize in many, I mean, the late John Conway was quite extraordinary. You know, he just visualized hugely complex combinatorial structures. And it's something I wonder is, have you done studies of these kinds of extraordinary individuals with these extraordinary capabilities for dealing with patterns or number? Or...
Okay, so I think we are over time here by about 5 minutes. There's right now a break, and we will reconvene at this address at 12:30. Yeah, it's going to be concentration of machine learning capabilities and open source options. It's going to be moderated by Terry Tao, and Stella Biderman is going to be talking. So see you all in 20 minutes, 15 minutes. Thank you, Stanislas and Ursula. It was fantastic.
Thanks very much.
Recording stopped.
Terry, I'm gonna.
But okay, thanks.
Amisha, are you here?
So Brittany is subbing in for Amisha.
Oh, that's right. Brittany, could. Maybe I'll put them up this time. Just for a second. Hi all, so we are back. Very quickly, I'm going to reintroduce everyone to Slido if you're just joining us. So
Recording in progress.
So just to give everyone a quick refresher, please submit your questions to the speakers and panelists, and we'll do our best to address as many as we can in the Q&A portions. So you can do so by going to slido.com and typing in AI for Math 23. And with that, I will hand it over to Terry.
Okay, thank you. Welcome to the afternoon session. My name is Terence Tao. I'm the moderator. So our first speaker will be on the topic of concentration of machine learning and open source options. And it will be given by Stella Biderman, who from Booz Allen Hamilton and Luther AI. Specializes in natural language processing, ML interpretability, and AI ethics. Stella's work has focused on making cutting-edge AI technologies more widely accessible through supporting the release of several of the world's most powerful generative models, such as GPT-NEO-X, Bloom, VQ-GAN Clip, and OpenFold. So, Stella, if you could do your presentation.
Hello. I think I need to reshare my screen actually to make the slides appear. One moment. Hello. As Terry said, my name is Stella Biderman. I'm here from Booz Allen Hamilton and the Luther AI to talk about kind of the landscape of machine learning. And when I say machine learning capabilities, I'm mostly talking about the large scale generative AI technologies, text models, text image models, stuff like that has become very popular. Yeah, I work at Booz Allen Hamilton and Luther AI, and mostly what I have been doing for the past 3 years is training very large and very powerful open source language models. Mostly in the text domain, GTP-Neo and GTP-Neo-X are two examples of what were at the time the largest open source language models like GTP-3 in the world. Bloom is a very powerful multilingual model, as well as some stuff in other domains. So OpenFold was a open source replication of DeepMind's AlphaFold 2 algorithm, and VQ-GAN Clip was a early text image model that I helped work on. So centralization, and when we talk about centralization of capabilities, we're also ultimately talking about access. That's also going to be an important part of this. So what are we talking about when we say that machine learning capabilities are highly centralized? Well, there's a couple of things that are being centralized here. First of all, there's the actual capabilities themselves, the models, which are overwhelmingly owned by a handful of for-profit companies. We're also talking about other kinds of centralization. There is extreme centralization in funding, in political influence and power. as well as simply in attention from other researchers, as well as from the media, in terms of who gets attention, as well as ultimately credit for the research that they do. Part of the reason for this is that breaking into large language modeling research is really hard. It's really expensive by the standards of most academics, and really has reached prices that were unprecedented in machine learning even a handful of years ago. If you want to train like a good model, like comparable to the original G2E3, that's going to cost you about $1 million. If you want to train a really good model, comparable to like G2E4, that's going to cost you about $10 million. And when I say cost you, I'm talking solely about the computing costs and the data of the final training run. I'm not talking about the testing. I'm not talking about the staff costs. Just the actual materials and resources you need to put together to build these models will run you between $1 million and $10 million. And if you're looking to get into this field, if you're looking to start up a new organization, if you're a university that wants to start training their own models, it will easily run you 10 times that. Part of the reason it's so difficult to get working is that there's just a lot of specialized knowledge that's not typically found in the NLP community that's required to really train these models. And there's been a lot of knowledge transfer from high performance computing organizations, but it's definitely no coincidence that the overwhelming majority of organizations that train these models are large scale computing companies that have large computing clouds and have been orchestrating large scale operations for a very long time. The overwhelming majority of AI researchers have never trained a model that requires more than 4 GPUs in their life. And, when we're talking about training these very large models, like a 20 billion parameter model, you want ideally a couple hundred GPUs for that. For a 100 billion parameter model, you're talking about wanting, 500 to 1,000 GPUs to make that happen in a reasonable amount of time. And this is just a knowledge set that's not very common in the AI community. And of course, there's the GPUs themselves. There are H100s are the latest and greatest thing from NVIDIA. There is a waiting list. There was a waiting list before they even came out. There was a waiting list the day that they were announced. And it's very hard for most groups, be them companies or smaller companies or universities or other researchers, to get access to kind of the state of the art and the cutting edge of computing. And this kind of reinforces a lot of the previous problems. So each new generation of GPU substantially cuts the costs to train models because the capability increase outstrips the cost increase. So, if you train a model on H100s, it's going to cost you like about 50% less than if you trained it on the previous generation A100s. And those are going to cost you about half of what it costs to train on the one before that, V100s. So G2E3 was originally trained on V100s. And in the past 4 years since that model came out, the cost of training that an algorithm like that has gone down by a factor of 3 solely in terms of having access to better GPUs. But like I said, there's a small number of organizations that ultimately control the supply and access to these things. So these are a lot of the reasons why the centralization happens. One of the really interesting impacts in the way that the centralization impacts most researchers is that it influences what people actually have access to. So there's a spectrum of release that people have for large-scale AI technologies. The most permissive are open source models that are released and anyone can use them for just about anything. There's a variety of limited use, which typically constrains commercial use, but not always. There's some other limited use license that people put out. Some organizations train and put out APIs where you can't actually download the model, you can't actually fine-tune the model, you can't actually use the model on your own systems, but you can pay them to run it for you. And then there are privately held models. Most of the most powerful models are either privately held or were originally privately held, and then sometimes a year plus after they were developed were released as commercial APIs. And this is really a huge bottleneck in terms of actually making AI research do work for the scientific community writ large, because privately held models are accessible to a handful of people and their friends. And the more people build on those kinds of models and the more people use them to do research, that research is kind of on a fundamental level not practically useful to almost anyone. So here's the same information displayed a little bit differently. Generally speaking, when people say open use, they're talking about the top two versions, while closed and commercial use are the bottom two. So here are some examples of well-known models and kind of where they fall. So T5, GTP-NUX, Pythia, Falcon is a very recent addition, are kind of the premier open source models. There's a variety of limited use models. These are models that, like I said, you can download them, but there's restrictions on how you can use them. You can pay OpenAI or Google or Microsoft or several other companies to use their APIs. And then there are some very powerful models that are privately held, and only people at the companies that produce them or the people who work with them can actually get access to those models. And it's also worth noting that even when we're talking about the most permissive stuff, even the open source stuff is highly concentrated. This is a list of every organization that has ever trained a 13 billion plus parameter large language model and released it publicly. There are, I didn't count this ahead of time, 2, 4, 5, 6, 7, 8 organizations on this list. 5 of them are United States-based for-profits. 2 of them are non-US for-profits, and 1 of them is a nonprofit. And so, even when we talk about releasing large language models and open source as a way to democratize and give a broader community of people access to these technologies, it does come with a pretty heavy caveat that they are still being produced by and shaped by and ultimately to serve the needs of a handful of organizations. So why should you care about this? Like, how does the concentration of machine learning capabilities and limits of access impact people who want to use these things to do research? So there's a bunch of reasons one might care. You might have ethical beliefs about what people should be doing with scientific research and scientific tooling. Financial ones. It's expensive to pay to use these models if they're going to be a part of your everyday workflow. And then as there are limitations on kind of what you're allowed to use them for and as well as who produces them, this creates a small concentration of individuals who are able to create these models, and therefore a small concentration of individuals who get to make a lot of decisions that matter in terms of what technologies get developed and what technologies don't get developed. So a really good example of this is language. What language a model speaks. There are a couple of models that are trained on kind of generically multilingual text that's been scraped from the internet. Of the models that don't fall under that category, almost all of the state-of-the-art models speak English, and like 90% of the ones that don't speak Chinese. There are really like 2 in Korean and 1 in another language that doesn't officially exist yet. But if you're someone who doesn't speak English or whose primary language of work is not English or Chinese, it's extremely difficult to actually get access to anything that you can use because, like I said, the overwhelming majority of the 50 largest language models in the world, there are 2 that are monolingual and don't speak Chinese or English. And another big reason to care is that level of access controls adoption. So here are 2 examples of really, really cool papers. This is not a slight on the researchers who did this. I think that both of these works are phenomenal and really cool. The problem is that nobody's ever going to use them to do anything. And the reason for that is because no mathematician is going to get access to them. So Balder was a paper by one of the organizers of this event, Talia and some of their colleagues on proof generation and repair. And then this other paper introduced a model called Minerva, which is allegedly extremely good at doing a whole bunch of mathematical reasoning tasks. And we have no reason to believe that anyone outside of probably 50 people will ever get access to either of these models. And I think that's really a shame. And that is ultimately one of the biggest reasons why you as a researcher should care about these differential levels of access. The more that people put investment and money and work into developing systems on top of unreleased closed source systems that there are no plans to ever release, the more really cool stuff that happens that is ultimately like a existence proof where, it's out there, that it can be done probably. And that's really it. It's never going to impact you. It's never going to allow you to do any research. Something that 6 months ago would have gone on this list is AlphaFold 2, DeepMind's protein folding algorithm. But as one really interesting thing that we've seen is that as open source capabilities kind of approach the state of the art, companies kind of decide to cut their losses and release greater access to their models. So a couple of months before the first open source replication of AlphaFold 2 came out, DeepMind decided to license it for non-commercial use. And so since then, there's been a huge amount of use of this model for scientific research by biologists and chemists that did not have access to it for, I think, about a year, simply because the model wasn't released at all. And so the last thing I want to touch on is kind of open source options. While I was talking with some of the organizers, they mentioned a fear that open source technologies are not very user-friendly, are difficult to use, and that even if they might theoretically exist, it's difficult to use them. And that's, I think, really fortunately not true in this particular domain. So I wanted to tell you a bit about that. So first of all, there's really a thriving open source ecosystem at this point. If you want data sets, we have data sets. If you want code for training very large language models, we have code for training very large language models. Fine-tuning, including parameter efficient fine-tuning or reinforcement learning from human preferences, evaluation code bases, as well as deployment. The Hugging Face Hub is a really cornerstone of the open source LLM movement, where I believe what they call themselves is GitHub, but not for code. And what they mean by that is that anything that it's roughly speaking structured like GitHub, but anything that's not a code base that you want to be able to use in large scale AI, you can get from there. So you can upload models and share them with people. You can upload data sets and share them with people. And it's kind of become the de facto standard place for people to exchange their models and such, as well as other kinds of deployment pipelines and ways that you can put these things into production. And I was going to have a couple slides showing how easy it is to use some of this code, but I figured an actual demo would probably make more sense. Can you still see my screen, or do you see the slides?
Yes, I see your screen.
Cool. So this is a GPU cluster that I've been using for some stuff. So this is an example of how to load and run a model from the Hugging Face Hub. So we have a couple import statements. We have one line that specifies which model we're trying to load. So it's the one by Luther I called Pythia. Some information about the data type. And here you can tell it what device to run it on. And if you want to run a sample on text, you can put in whatever you want. So this is a cool example, is what their demo had. So let's go with that. And it takes a bit of time because you have to, these models are slow to load onto a computer because you have to load a large amount of data and then transfer it from a CPU to a GPU. So the time that we're actually waiting right now is nothing to do with running the model up the rail. Almost all that time was simply loading it onto something. So if you're using this in a continuous fashion for many prompts and many generations, it goes much quicker. You have the same kind of startup time, but then each generation takes a second or less. And you can generate text. And if you want to use a different model, so if you don't want to use Pythia, if you want to use a model called OPT that Meta released, it's really just a matter of subbing out like the name of the model for the name of another model, and it will just run right out of the box. And you can kind of use and manipulate these things really similarly to how you do any kind of deep learning training. Writing training loops is very straightforward and basic. Pipelining, my apologies, pipelining data out of it and into other systems is very straightforward. You can see that the text generated is a little bit different because it's a different model. Yeah, and also wanted to just give a quick peek at, move this out of the way. this is the Hugging Face Hub I had mentioned is one of the key parts of the open source ecosystem. So you can go and this is my organizations page, and you can see various models that we've released, and you can just download them, and thousands of people do. It's early in the month, but you can get information about licensing, about tons of information, details about the models, and pretty much every openly released language model out there can be found in this database and loaded using their library, which is really a impressive feat of coordination at the end of the day. We have, like I said, we have evaluation code bases, open source leaderboards that people have put together to evaluate models on different tasks. You can run various evaluation tasks yourself, and there's really amongst open source developers, there's a really high focus on interoperability. So if you take code that Luther I wrote, you can run models that Facebook has trained. You can run models that Hugging Face has trained. There's like I said, a very high focus on making it all work together. So yeah, that's kind of the current state of the ecosystem of open source and also closed source models. And I want to just take the rest of the time to answer your questions and learn a bit about how you want to use AI and kind of what's preventing that from going successfully right now. So we have these models, they're out there obviously. And yeah, I'd love to answer some questions if people have them or similar, and figure out how to stop sharing my screen.
Okay, thank you. I think I'll start with one of the questions from one of the organizers. So Talia asks, what advice would you give someone who's leading a new large open source AI effort organization, given what you know now?
That's a kind of a strange question. It's a very interesting question, but it's a bit of a strange question to answer because.
Well, like maybe what kind of priorities should an open source project have, and or what pitfalls should one avoid? Like, do you have some insight into why some projects succeed better than others? Maybe.
So when it comes to open source stuff, and this is more general than AI, when it comes to open source communities and open source efforts, being able to actually build a community is really a massively important part of getting things going, both in the early days as well as maintaining it as you grow. So Luther AI is an open source community, and we have a public Discord server with hundreds of daily active users, many of whom submit code contributions, participate in our research, and talk about AI alongside us. And having their assistance and support is really an essential part of maintenance and keeping up with the extremely rapidly moving and changing field. Yeah, I would say that focusing on building a community that you can rely on, and I mean, managing volunteers and such is definitely a interesting challenge in and of itself.
Yes. I can imagine.
Yeah, writing a paper with like 20 authors, 15 of whom are volunteering their time on the side of their job is definitely a challenging experience. But it's a fun time. And yeah, it's really important to figure out how to get that going and build interest in community so that people keep coming back and keep contributing.
Okay. Maybe building on that, there's a question from Slido, like what can be done culturally to encourage people in the open source community to collaborate, and how can one prevent the community from being co-opted by other interests?
So there is a huge amount of collaboration in the open source AI community right now. We all know each other, or we all like each other. We share tools, we share advice, we share research projects while they're under development. There's a huge amount of collaboration and cooperation across communities. Where kind of the communication breakdown often occurs is between open source research efforts and for-profit companies that don't particularly encourage open source, or even just the research groups that don't do open source work within those companies. So some companies engage in both open and closed source research, and the results and the things that they find and learn with their closed source efforts are often not shared or broadcasted really at all to other researchers outside of their group. In terms of the open source community kind of more broadly than AI, I would love to get them more involved in open source AI stuff. There is a huge need for open source developers who don't know almost nothing about AI to contribute to a wide variety of tasks. I actually gave a talk about this basically begging people to come help us out at the Linux Open Source Summit last month. There's a huge amount of infrastructure, there's a huge amount of work that underpins the development of these large-scale AI systems and the sharing and deployment of these large-scale AI systems. It ultimately is kind of your standard software engineering or data science type stuff. And you don't need to be an expert in AI, let alone large-scale AI, to write evaluation libraries, to contribute to Docker and Kubernetes and queuing systems. There's just so much stuff to be done that there's really a strong need for more people to come and if contributing to open source AI is something you're interested in doing, you can absolutely do that without any particular knowledge of AI and pick it up as you go.
Okay, thank you. James asks, are there any large language models that are widely available for mathematicians, ones that have been trained on, say, archive papers, mathematics textbooks, and so forth?
Repetitions?
Sorry, are there any large language models that are widely available to mathematicians? Are there any models that are specific to math or science?
Yes and no. There are a number, it's actually very common to train large language models on mathematical texts. So archive is a very big source of this. For science more broadly, people use data from PubMed, people use data from a variety of preprint repositories and stuff like that. That is kind of baked into what is the current standard for training a large language model. You go and download a roughly state-of-the-art model. It's almost certainly going to be trained on archive. It's almost certainly going to be able to produce LaTeX. It's almost certainly going to be able to interact with mathematics. In terms of models that are specifically designed for that purpose, there are two that really stand out. One of them is called GOAT, which is a fine-tuned version of a model called Llama that is focused on really precisely getting computations correctly. So when these models are trained on very large corpus of text, most of the data that they see has nothing to do with like 17 plus 82. And so it's not really something that the models tend to put a lot of effort into learning, even though we know that they can learn arithmetic. We actually know that they can learn arithmetic perfectly. But they don't tend to be perfect at arithmetic because they have just seen so much other data. So people have been fine-tuning models to be much better at arithmetic. And when I say arithmetic, I'm speaking here more broadly, matrix operations and all sorts of computations. And then the other one is a model developed by Meta called Galactica, which was trained exclusively on scientific corpora, and which they at least originally advertised as being an assistant for writing scientific texts and for answering scientific questions. Those are kind of the two models that jump out immediately. I can drop links to where you can download both of them because it's all very readily available.
Thank you. Let's see. Lars asks, so is there anything that the US government could supply that could encourage AI research? So one suggestion here is to have US government challenges in which solvers are provided with some GPU cloud resources to reach some sort of scoring target. So where the model, where some of the compute maybe is provided.
So the number one thing that the US government can do is put together and release a data set. The entire large-scale AI community is in a legally awkward situation where people kind of have this presumption that training language models on data that you download off the internet is fair use, or at least is not going to be something you're going to get in trouble with because everybody does it. But especially for smaller organizations, and especially for people who don't necessarily have, an army of lawyers, there's a huge barrier to doing work that involves being transparent about your data sourcing for this reason. So the first large AI project I did was I put together a data set of mostly license compliant text and put it online. And so a lot of people have come and asked me questions about using it. And we put a lot of effort into documenting where we got our text and what license all the components are under and stuff, so that people can make an informed decision about what they're going to do with it. It's less that people come to me and say that they don't think that they can use the data set. It's more that they come to me and say that they don't know if they can, and they are very afraid of a lawsuit ruining them. If you look at kind of the corpora that, at least for the models where the companies disclose where their data comes from, so that's not a given. When large companies train models, they tend to be a mix of sources that are very carefully hammered out by the company's lawyers. Like, these are the things that we feel comfortable using, or these are the things that we feel comfortable defending using. And so really just like the uncertainty of it all is a huge bottleneck. There is no publicly available data set that is known to be fully license compliant, and for training a large language model on, that is of the scale that you can train a model with several billion parameters on. That's just not something that exists. It's something my organization has been working on doing. And it turns out that finding several billion characters or words of text, or sorry, several hundred billion words of text is really, really hard. Especially when you put really strict license compliance rules on it. For most organizations, access to compute is a major limitation. But honestly, I mean, I come from a very strange place, because I come from probably the best funded, from a compute point of view, the best funded research organization in the world in this space. We have tons of GPUs. We train models with tens of billions of parameters all the time. And so I don't feel super comfortable speaking to exactly how their bottlenecks work, but there's definitely a need for more GPUs and for payment for more GPUs. My understanding is that a lot of these organizations that need said GPUs also have a need for kind of HPC expertise alongside them. So which is really a bottleneck when you don't know, training a model on multiple nodes is just a fundamentally different endeavor than training it on one GPU or even a small number of GPUs. And so the GPUs, I think, are definitely going to be very useful to most people, to most researchers, but really having some kind of support alongside it would as well.
Okay, well, thanks very much for your time and your questions. So we need to move on now to the next session, which is on mathematical foundations of machine learning. So we have two speakers for this session. First is Morgane Austern, who is an assistant professor for the Department of Statistics at Harvard University. She's interested in understanding the behavior of algorithms and statistical estimators in the presence of a large amount of dependence. Work consists of developing probability tools, new probability tools, and using them to establish properties of learning algorithms in structured and dependent data contexts. And our second speaker will be Rebecca Willett, who is also a professor of statistics at computer science at the University of Chicago, where she's a faculty director of AI at the Data Science Institute and leads the AI plus Science initiative. The research is focused on the mathematical foundations of machine learning, computational imaging, and signal processing. So Morgane, I think you are going to go first, if you can begin.
Hi, everyone. Can you hear me?
Yes, I can hear you.
So let me share my screen. Or are you sharing the screen because I sent a slide? I'm not sure.
If you can share the screen, I think that would be the simplest.
Okay. Okay, I'm going to share the entire screen. This is just going to be simple. Okay, can you see the slides?
Yes, it looks good.
Okay, great. Hi, thank you for the invitation. So machine learning algorithms are increasingly aimed to be used in critical settings and high-stakes settings, ranging from medicine to the justice systems. And in both settings, making errors in the prediction can have severe consequences, especially when those algorithms are used then to make decisions. And so it's crucial to be able to know how much we can trust those algorithms, how much confidence can we have in the predictions of those algorithms. So mathematically, this can be formulated as wanting to quantify the uncertainty that we have about the prediction of a machine learning algorithm. And related but different, we can ask not only do we know how much certainty we can have in the prediction of a certain machine algorithm, but does the machine itself know? So like, does the algorithm itself knows? And so this is becoming of, and so this is called calibration, and this is becoming of increasing interest, especially with the rise of large language models. So I'm going to just do go through a very high-level overview of those questions coming from a mathematical standpoint. We're going to go from first principles and then kind of dive on into some open questions. It's a common theme that you're going to see is that there are a lot of open questions. There's a lot of things we don't know, but we also have made quite a lot of progress. And so for everything that I'm going to talk about can apply to many different learning problems. For simplicity, we are going to zoom on in most of the talk on a very specific learning problem that is simpler to describe, which is classification problems. So those are supervised learning problems where your data come in form of pairs of observation and labels. So for example, the observation can be a picture and the label can be the type of animal in that picture. And your goal is to train an algorithm that will take as input a new observation, so for example, a new picture, and that will output a label. And so this is your goal, and we're going to call such an algorithm a classifier. So you got very excited and you trained your classifier. You chose your favorite machine learning algorithm and you trained your classifier, and you're very proud of it. And now you want to know how much you can trust this algorithm. And so, and the prediction is going to make. And so for the first level question that you might ask yourself is, well, imagine someone gives me a new picture, a new observation. What is the probability that my machine learning algorithm is going to misclassify this new picture? And so this probability is what we call risk, and it's one of the most fundamental quantity that you want to estimate in statistics and machine learning. How to estimate it? Well, the first naive idea that we might have is to look at your training data and to look at how many examples you might have misclassified in your training data. While this is a natural idea, it's actually a bad idea. You will tend to systematically be overconfident with the performance of your estimator. And this is because you're using the same data to train your estimator and to evaluate it. And so you're kind of cheating. So to go around this, one of the most used method in traditional machine learning is the k-fold causalization method. And so this consists into splitting your data into k different folds, then iteratively taking one fold out, let's say here the first one, then training your algorithm on the remaining folds, so here, for example, folds 2 to 3, and then evaluate the performance of your algorithm on the fold you just took out by computing the number of misclassified examples. And then you can put it back and then do the same thing for the second fold, etc., etc. And the k-fold quasi-validated risk is the average number of misclassified examples in this white part here. And so, as I said, this is in traditional machine learning, probably one of the most used methods, and it's known to be a valid way to estimate the risk. We notably know how to exactly quantify the precision and the uncertainty that we have about this estimator, and this was we done this very recently. So here I presented this when we splitted our data into 3 different parts. There is no special magic about the number 3. As we get more, we are trying to study more and more complex algorithms that are more and more data intensive. There's an increasing need to be able to, there's an increasing interest for instead splitting our data into n different folds. So here we're going to chuck our data into n different folds, and each one of our folds is going to contain exactly one observation. So this is what is called the live-on-out causalization setting. And the interest of this is that it is in a way more data efficient, because almost all the data is used for training our algorithm, which is interesting when our algorithms, are data demanding. And this was proven, contrary to popular beliefs, to actually be also the statistically optimal way to estimate the risk using cross-validation we did that in a very recent paper. So because of this, there has been also an increasing need, interest in trying to build new methods to be able to estimate this Levonard cross-validation way in a computationally efficient way. Okay, so you can take all of this, and now you know how to estimate your risk of your estimator. So notably, you know that modern deep learning algorithms can achieve extremely high accuracy on classification problems, but obviously they're not perfect. So for example, if you look at the classical ImageNet dataset, which is the classical dataset for training and evaluating classification algorithms, the current state of the art is about 91% accuracy, which is high, but is obviously not perfect. Obviously, if we had more data, we could go beyond this, but the point is no algorithm will get you a perfect prediction. And so knowing this, imagine that I give you a certain observation. An important question that you might have is, how confident can you be in the classification, in the labeling that it's producing? And one thing that people do notice is that neural networks naturally produce confidence scores. And so it's kind of tempting to want to use those confidence scores and to answer this question. Is this a good way? Is this a reliable way to try to measure the uncertainty about algorithms? How confident can we be? And how much can we trust those confidence scores? This is at the end of the day a calibration question. We say that a model is well calibrated if a model faithfully reflects its uncertainty. The bad news is that machine learning, deep neural networks are famously badly calibrated. They tend to be significantly overconfident in their prediction. So this is an illustration that I borrowed from this very famous paper here, but illustrated this for the ResNet architecture and showed that this neural network tended to be really overconfident in its prediction and almost always put a confidence close to 1. And so knowing that we cannot trust the confidence scores coming out of our neural network models, how can we try to build more reliable prediction? Well, one idea that has been proposed is that instead of just returning one label, maybe you would want to return a small set of potential labels. But that has this nice property that we know that the true label is one of them. So for example, instead of just saying, oh, this is a squirrel, maybe you're going to say, this is a squirrel, or any of those 3 labels, and the probability that the true label is one of those is very, very high. I'm very confident in this statement. And we would like to be able to do this even for badly calibrated machine learning algorithms or for black box algorithms that we don't really know. And this is made possible by conformal inference, which is a method that is currently gaining a lot of traction and attention in this literature. It was originally proposed in a series of papers that I'm citing here, and currently a lot of people, including me, are working in this direction. And it proposed something quite interesting, which is it proposed a way to build those set of potential labels, we're going to call those prediction sets, in a way that is reliable and that works even for miscalibrated algorithms. And so the answer is yes, we can exactly do this. And the way it's done is kind of similar to cross-validation. It kind of also uses some idea coming of splitting your data into 2 parts. One is used for learning and one is used for calibration. So there are ways to try to make your algorithm more reliable. We talked about calibration in the neural network setting. What about large language models? So this is a question that is currently attracting a lot of attention. And this is because of the fact that large language models are infamous with a tendency to hallucinate. And so we would like to know if they know that they are hallucinating, if they know what they know and what they don't know. And so at the end of the day, this is a question that we want to answer. So the first step question is trying to understand how well calibrated those algorithms are. Obviously, those are not classification algorithms. And so this notion of calibration is evaluated on a subset of tasks. So for example, giving it multiple choice questions, or trying to ask if a reference is real, or trying to take an answer that it created in a previous session and asking it if it's true or false. So those are the type of tasks that is evaluated on, because often now we don't have access to the models themselves. We only have access to the algorithm through an interface. For example, this is a case for ChatGPT. to try to know how confident the model is in its predictions, we don't have access to any confidence to anything about the model, so we need to estimate this. And we can estimate this through like repetitive prompting, and so which is kind of a way of sampling. And so this is a lot of people are looking at those questions right now. There's a lot of work. It's way too early to give any kind of conclusive evidence or conclusive findings. People are trying to understand what influences calibration, for example, the size of the large language models, the type of models that is used, the type of question that is asked and how it's asked. If, for example, giving a few examples of previous answers that it created, does it help or not? There's a lot of interest in this and a lot of experimentation going on. And there's a lot of interesting findings, but it's a bit too early to conclude anything. This is here looking at, for example, the effect of this model size. And it seems to say that large language models seems to be better calibrated. But once again, this is very early. Okay, so if we cannot trust deep neural networks to know their own uncertainty, can we instead use mathematical formulas or theorems for measuring this uncertainty? And this is a very appealing, question, but sadly, this is not really possible. And the reason for that is that our mathematical understanding of deep learning is still largely lacking. We understand some bits and pieces, but there's still a lot of mysteries. There's still a lot of things we don't understand. We don't have a full picture of what's going on. And so I'm not going to give you a list of all the mysteries because there's a lot of them. I'm just going to zoom on one that is probably the most related to what I'm talking about, which is the mystery of generalization. So this is kind of related in a way to reproducibility. So the classical learning theory is brought by deep learning. So what did this classical learning theory told us? It's kind of told us, followed the classical Occam razor that says that if you have multiple solutions, the simplest one is usually the best. And what in learning theory it means is that if your model is too complicated, you will tend to overfit to your data. And so you will tend to have worse predictive performance. And so here in green, for example, you can see this very wiggly line here. And this one is kind of this model has too many parameters, too much room to move, and it's kind of learning and overfitting to the data rather than learning the underlying pattern. And so the classical learning image that we all had was that as you increase the complexity, at the beginning, both training and testing loss decrease, but after a while you enter the overfitting regime, and while your training error might still go down, your testing error will go down. And so that you don't want to have a model that is over-parameterized. Deep learning is completely breaking all of those rules that we created. Deep learning algorithms are massively over-parameterized. They can have on the order of 10 to the power 9 different parameters. And we know that they have a capacity to arbitrarily overfit to any data. Yet, when you train them, often they do not overfit, and they tend sometimes to generalize quite well. And so this is kind of like, this observation was very puzzling and led to a lot of interest from the whole mathematical literature to try to understand why is this happening, what is breaking here. And so we kind of now understand that the picture for the learning picture for deep learning is kind of different, and that instead of we have this double descent phenomenon. There's also multiple descent, but here I'm talking about a double descent phenomenon. So once again, that's at the beginning when we increase, we start to overfit. But then once our model complexity crosses a certain threshold, then suddenly, as our model gets more and more complicated, our testing loss once again improves. And that means that suddenly having more parameters actually makes our model more accurate and testing error better. And so this was kind of surprising, and then really a lot of people in the mathematical community got interested in this. And this also has a surprising implication that it means that in certain regime, actually having more data can hurt. And so this is illustrated here for transformer models. And here this is one model that has been used, trained with 4,000 samples, and this one has been trained with 18,000 samples. And here what you can see is that there is a regime, there's a set of complexity of the models for which having more data seems to make your testing error worse, to make your accuracy worse. And so this was very surprising. And the big question is, can we explain this? Do we have an explanation for this? Well, since this was observed, we have also observed this in other more simple models, such as linear regression, logistic regression, and some very specific two-layer neural network. And we're able to build a theory for what happens in those models. And what seems to be happening is that is the concept of implicit regularization. So what I kind of like brushed under the carpet until now is how those models are trained. Those models are trained usually and chosen to be the one that best explains the data according to a certain objective function, a way to measure this. And when your number of parameters is quite small, you often have one unique choice. But as your model and your model gets more and more complex, you might have multiple choices of model that explain well your data. And how your optimization algorithm works, so how you choose which algorithm you actually choose, plays an important role. And we understand how this optimization interplays with this number of parameters for the simple model, but it seems that the same thing is happening for deep neural network. And we suspect that the specific way we are training our neural network through SGD is kind of explaining a lot of its behavior, but frankly, we don't know. We have theories, but we don't completely understand what's going on. And this is despite a lot of interest from the community and a lot of ideas that has been brought from different sides, from free probability to statistical mechanics, to physics, to information theory. And each one brought its own piece to the puzzle, but there's still a lot we don't understand. So let me kind of illustrate this with one piece of a puzzle that was kind of brought by information theory. So in this work, we use the fact that we know that two empirical observations coming from neural networks and combine them with information theory. So we use an observation that neural networks, after training, can be compressed to be a fraction of their size and still retain a lot of a predictive power. And also neural networks tend to be robust to small perturbation of their weight. And this is kind of saying something in a way about how complex, the complexity of your model. And so if you combine this notion of complexity with notion of complexity coming from information theory, we were able to get a first non-vacuous generalization bounds for modern deep learning architectures. But this is only one piece of a puzzle, really. And it is still a lot of things we don't understand. Before I conclude, I've been talking a lot about what happens when you are looking at a sequence of observation. Machine learning is increasingly used also for science discoveries. And often in sciences, we are looking at deeply structured observations, for example, dynamical systems in physics, or networks in biology. So for example, those are protein-protein interaction networks that biologists are trying to study to try to understand disease pathways. And in those networks, one thing that people are trying to understand is they are trying to predict, they know that certain proteins interact together, and they're trying to use machine learning to try to predict which other protein could interact together. And so there's a huge interest in trying to use machine learning for those different scientific questions, notably on those structured data. Now, the problem is obviously that those type of very structured data, such as graph data, are not really amenable to the use of machine learning tools. We cannot directly use a machine learning tool on those data. And so the idea is to try to represent them in a way that is more amenable for machine learning. And so, for example, to represent every vertex by a point in a d-dimensional sphere that will present this vertex and its position in the graph. And so the hope is, for example, that two vertices that are close together in the graph will be represented by points in the d-dimensional space that are also close together, and points that are far away in the graph would also be represented by points in the d-dimensional space that are far away. And so that this representation would be a good representation of the network structure. And the point is that once you obtain those embeddings, this representation of your graph, which is a very discrete structure, as a sequence of points in a d-dimensional space, then you can use classical machine learning algorithm to try to study and do machine learning on those objects. So this is the point of representation learning. And the key nerve of the whole is trying to find good embeddings, good representation of your graphs. And this is what many graph representation learning algorithms, such as Node2Vec and graph neural networks, are trying to do. Now, the key question is, do those algorithms generalize well to unseen data? Can we have a notion of uncertainty quantification for those? And honestly, we don't have a good answer. All of those questions are really poorly understood in the case of when we are working with structured and dependent data. And the reason for this is twofold. First one is when you're asking a question about uncertainty quantification, you're asking something about new data. So you need to have a model of the world of how new observations, so here new vertices and edges, would appear. And the second point is that those new points and the new vertices will not be independent from the current graph. So you need to take into account the structure of the graph and the dependence when you're building uncertainty quantification. There's some beginning of answers, and we were able to get some partial answers that led to better algorithm, but honestly, there's a lot that is not understood. So for the interest of time, I'm just gonna go to my conclusion, which is there is a lot we still don't know about the mathematics of machine learning. Honestly, there's a lot of open questions. And why is that? This is because we don't have the right mathematical tools to study those algorithms. The classical learning theory really relied on a few powerful universal theorems. And what I mean by universal is that they hold in the very general settings. But the problem is that those theorems don't extend to the modern machine learning algorithms. They just don't apply. And so we need new tools. We need new mathematical theories and new universal theorems. That's the only way that we can build a universal understanding of machine learning, is if we have new powerful universal tools. And so we need new mathematics. It's something that I've been really working on a lot and that I'm very interested in building. But honestly, this is an invitation to the entire mathematics community to kind of bring that stone to the edifice. I think a lot can be contributed from very, very different fields in mathematics. Notably, I have used tools from functional analysis and algebra in my work. There's a lot to do here. We really need new mathematics, and I think this is a great opportunity to kind of contribute and try to understand better what is happening with those machine learning algorithms. Thank you so much for your time. I'm going to conclude, and I'm going to let the other speaker speak.
Thank you very much. We're going to move on to Rebecca Willett now to give a second talk.
Great. All right, can you see my screen and hear me?
Not on your screen yet, we can hear you only.
Oh,
your camera has been aimed down towards your keyboard, just so you're aware.
All right, how does this look?
Yeah, that's good.
Great, thank you very much. It's a real pleasure to be here with all of you today and to be a part of this, I think, really exciting and interesting workshop. So, like Morgane, I want to talk about some of the mathematical foundations of machine learning. And to start off, I wanted to make the point that investing in applied machine learning research without really understanding the mathematical foundations is akin to investing in healthcare without understanding biology. By really understanding the foundations, we're going to be able to develop systems that are faster, cheaper, more accurate, and more reliable in a variety of different contexts. And so what I'd like to do today is to basically cover two main themes. First, I want to cover some examples of settings in which we have had real successes with mathematical foundations leading to improvements in the practice of machine learning. And then second, I want to talk about some of the opportunities for answering open mathematical foundational questions and their potential for impact in the broader community. So first, let's look at a few different success stories. So often when we're running machine learning, our task is to fit some sort of model to training data. And when I say that, what I mean is that a model typically has a bunch of parameters. We can think of these as like the weights in a neural network. And we need to choose the set of parameters that best fit our training data. Typically, this is done with an optimization algorithm that's trying to minimize our errors or some loss function in an iterative approach, where at every iteration, we update our parameter values. And the way we figure out how to do these updates is based on decades of optimization theory. And typically we use what are called gradients of the loss. So you can think about this as a higher dimensional derivative. So one more recent innovation in the context of optimization is something called Avigad, which says when we're computing these gradients, we should actually adapt them to all of the past estimates of parameters that we computed in previous iterations. And that by doing this, we can actually accelerate the training, make the whole optimization process significantly faster. So this method has strong theoretical grounding. We understand it very well. And in addition, one of the most popular optimization methods used for training neural networks, ADAM, is based on the foundation of Avigad. Another example relating to optimization is dealing with distributed optimization. So if I'm training a very large scale system like ChatGPT, which Morgane just mentioned in her talk, I've got huge amounts of data and huge models. And so to train this, I would want to distribute this across multiple different computers that can do some of the gradient updates or the computations. And our expectation is that if we throw more computers at this problem, then this whole optimization and training process will be much faster. But in early days, people experimented with this using naive distributed optimization methods. And what they observed empirically is that as they tried to increase the number of machines, the whole process actually got slower. And so people studying this mathematically and theoretically as well as empirically noted that the bottleneck appeared to be the amount of communication that needed to take place among these different nodes to keep them all in sync with one another. But by really understanding optimization theory, we were able to develop, we as a community, were able to develop new approaches, with Hog Wild being an early example of this, that were theoretically grounded methods for asynchronous distributed optimization. So they basically eliminated the vast majority of this communication bottleneck and used the foundations of optimization theory to show that this wasn't going to cripple our training systems. And empirically, we were able to see that with this method, we got much faster computation as we added more machines, as we would hope for. Another success story is in the context of privacy. So when our training data is human-centric, we want to make sure that when we train a machine learning system on that data, that we're protecting the privacy of the people represented in that data set. So a classical approach that we've seen in many places, including in various laws and government regulations, said in order to protect people's privacy, what we need to do is we need to aggregate the data. So for instance, there'd be a rule that says you can't release the data of any individual person, but as long as you were to compute an average over 10 or more people, those averages can be released to the public. But unfortunately, we can use mathematical foundations in order to show that without more conditions on how the data is released, this form of privacy is actually very easy to break. It's extremely fragile. But a more recent innovation, again, grounded in the mathematical foundations of machine learning, is differential privacy. So the idea here is that we add random perturbations to our data. And we do this in a careful, theoretically grounded way that allows us to guarantee that someone looking at the output of our algorithm, say of our machine learning system, is not going to be able to tell whether any individual person's data was used to train that machine learning system or not. And here I've just got a little kind of tongue-in-cheek example where you could imagine this being a data sample. And as we add more and more random perturbations, we can see that we're masking more and more personally identifiable information. And these ideas grounded in theory have had enormous impact across the board. Another kind of success story is something that Morgane explained very eloquently in trying to quantify uncertainty associated with the predictions made by machine learning systems. And so I don't want to reiterate what she said, but I do want to just point out that there were classical methods that would assume that we have a very simple model, something far simpler than modern neural networks, or had very strong prior knowledge. And these things are just not workable in most modern contexts. But the kind of foundational work in conformal prediction that Morgane pointed us to allows us to assess uncertainties without these really huge assumptions or constraints, and with nice theoretical guarantees. The final success story that I want to point to is related to a specific application, medical image reconstruction and other similar types of problems. So imagine, for instance, that I have raw data coming from a CT scanner, and it would look like this. This is called a sinogram. And what I want to do is I want to take that sinogram and produce an image that a radiologist can look at. And so people ask, well, can I just use a neural network to train a neural network to actually take that sinogram and produce an image? And some of the early efforts did this exactly the way I described, just sort of naively used a generic neural network architecture. And it worked, but it just required an enormous amount of data. And in part, that's because it totally ignored all of our knowledge of how the CT scanner works. Right? We actually know the relationship between this sinogram and this image, and ignoring that information forces the neural network or the machine learning system to learn that information. So it turns out that if we use this knowledge of how the CT scanner works and draw upon mathematical foundations from areas like inverse problem theory or optimization, we can actually get new neural network architectures that are designed for this kind of task and are more accurate with far less training data. So I want to emphasize that all of these kind of success stories and advances that I've just described are, first of all, isolated examples. There's a wealth of different settings in which understanding mathematical foundations has made practice more efficacious. But in addition, they all depend on just decades of foundational research in areas like optimization, statistics, information theory, and signal processing. And these theories were developed without specific applications in mind. And so this is evidence that investments in mathematical foundations is really worthwhile and important and impactful. Okay, so with these success stories in mind, I also want to point to some of the ongoing research directions in the community, the associated open questions, and where I think there are some particularly exciting opportunities. So to start off, I want to say something that's maybe a little bit more abstract, but I think really important to understand, which is that neural networks fundamentally are functions. They take in some sort of input data point, in this case, some d-dimensional thing. You could think about this as like an image, for instance, with d different pixels. And then it produces an output that, of course, depends on the input. And it also depends on theta, the values of all of the different weights in this neural network. And so what we're doing when we train a neural network is we are trying to find a good set of these parameters, theta, like I described before, so that it fits our training data. And so one way to interpret this is that what we're doing is we're searching over different functions. And so by thinking about neural networks as functions, lots of different open questions and challenges, but also opportunities arise. So to be a little bit more concrete, here's an example in 2D. So I've got x1 values and x2 values, and these two pictures here correspond to two different functions. So if I look here at a particular point in this plot, the color tells me what the output of the function would be. So in blue, the function output is low, and yellow, the function output is high. These two functions that I'm showing here are both exact fits to the training data located at all of these different little circles in the plot. And so now we can say, all right, well, when I train a neural network, when I'm searching for these weights and I'm basically choosing a function to fit the data, what type of function am I actually choosing? When will I choose the top one? When will I choose the bottom one? When will I choose something else entirely? And what determines which function is going to be selected? By trying to understand these questions, we hopefully are going to be able to address a plethora of other kinds of very important questions. such as how much data and what kind of data is required to optimally train these systems, or what models are appropriate and how big should they be? What can we do to promote robustness so that small perturbations in the data don't give us just wildly different results? And will models trained in one setting still be effective in slightly other settings? And so the hope is that by understanding how to think about neural networks as functions, we'll be able to have a toehold for answering these very important questions. Relatedly, there's been a number of different stories outlining some of the environmental impacts of work being done in machine learning, the huge carbon footprint associated with training and deploying different large-scale AI systems, or the amount of water required to cool the different computational systems used. The hope is that by understanding the mathematical foundations of machine learning and things like these function space perspectives of neural networks, we're going to be able to optimize architectures and the way that we train, including some of the information theoretic tools for model compression that Morgane highlighted in her talk a few minutes ago. Similarly, I think all of us have seen stories in the news about some of the downsides of this modern AI world, where we have to worry about systems that are biased against different groups, or the ease of propagation of misinformation or other adversarial information. And these kinds of stories have spurred the call for regulation and certification of AI systems. People have proposed things like knowing where the data comes from, or making sure that an AI or machine learning system is interpretable. And depending on the context, these are good things that we should not discard. But I also think that they are very far from sufficient. And so one of the core mathematical foundational open questions that we as a community face is, how do we design meaningful regulations and certifications of machine learning systems? And how can our understanding of this mathematical foundation help us ensure that these regulations and certifications are enforceable and meaningful? So finally, I want to talk about one domain where we see machine learning being used increasingly broadly in really exciting ways. And this is in the context of scientific research. So we're already seeing that machine learning is just changing the way that people approach scientific research. It's, of course, letting people do new things with analyzing scientific data, but it's also influencing the way that people generate new hypotheses or simulate different experimental regimes, or even design new physical experiments. And doing this properly is extremely important. So there was an article in Wired that highlighted how the sloppy use of machine learning is causing a reproducibility crisis in science. And the core message here is that people are taking off-the-shelf AI tools without fully understanding how they work, because we lack the mathematical foundations, as Morgane pointed out, and then using them in order to produce results that we can't always trust. And so there's just this wave of spurious results. Now, despite this word of caution, I think that the combination of machine learning and scientific research is an area with just enormous potential, both in terms of inspiring mathematically foundational questions that we can address, and in terms of potential impact. And so I just want to highlight some of those examples of that briefly. And I'm going to talk about 4 kind of key examples: uncovering new laws of nature, using machine learning to guide the way we collect scientific data, using physics to inform the way that we design machine learning systems, and advancing machine learning frontiers in ways that are inspired by scientific challenges. So first, let's talk about uncovering new physical laws. So in other words, given observations of a system, we want to use machine learning to understand the equations that govern that system. So here's an example toy system that we can think about to just sort of spur our thinking. I've got 2 different particles that started at almost exactly the same point. And the way that they're moving over time is governed by this system of equations describing its X, Y, and Z coordinates. And so we can see how these particles change over time. But as a thought experiment, you might say, well, what if I had scientific data of this form? I get to observe the locations of different particles over time. And what I want to do is go from that raw data to an understanding of what these equations look like. So can we learn these governing equations from data? And there is some work, some very interesting and exciting proof of concept work showing that in a variety of settings, we can in fact do this. Some early work posing this in terms of linear systems, sparse linear systems, and as well as more recent work using more advanced and modern machine learning tools. But throughout all of this, there remain significant mathematical challenges, generalizing these ideas to high dimensions, dealing with sparse or missing or noisy data. And this is where really developing the mathematical foundations of machine learning can be enormously important and impactful. And if we can do this, it's going to have impacts beyond just the mathematical sciences. It's going to help us rethink biophysics by understanding forces related to cell development. It's going to give us new insights into polymer physics, the way that different microbial communities respond to their environment and what makes them resilient, or even trying to understand emergent behavior coming from agent-based models, like the models that we use to predict how people would respond to different COVID policies. The second pillar is using machine learning to better design experiments, simulations, and sensors. So let's imagine that I wanted to design a microbial community that will serve some purpose, like it's going to improve the human gut microbiome, or the community is going to degrade plastics for us and help the environment. So I want to design that community to be as effective as well as long living as possible. And so I call this fitness. I want to fit a microbial community. And that fitness is some unknown function that I don't understand that depends on the population density of different strains, how many nutrients are available, what kinds of toxins are present, and what the environmental conditions are. So to try to maximize this fitness, I could just test everything, except that would be enormously expensive. There's just too many possible combinations to test them all. I could also just try to experiment totally at random, but that means using experimental resources in areas that might be very, very far from the maximum that we seek. But foundational work in areas like active learning and bandit methods are enabling us to use AI and machine learning to guide the development and design of sequences of experiments and find maximally fit communities. And more broadly, there's a whole sub-community that's interested in developing what they call self-driving laboratories that are adaptively designing and conducting experiments in high throughput situations in a variety of different contexts and applications. We're also interested in leveraging physical models and experimental and observational data jointly. And this arises in a number of different systems. One example of this is trying to develop emulators of solvers of large-scale PDEs. So for instance, when people develop climate simulations, they're basically solving large-scale systems of PDEs from first principles. And these are very effective, but they can require supercomputers and millions of dollars to run. Developing machine learning methods that emulate this process, they can run much faster on a desktop, which is super exciting. But these empirical proof of concepts really lack solid mathematical foundations at this point. We don't really understand when we can expect them to work or when they're going to fail. We don't know whether they're going to learn everything about a system or whether they're going to totally ignore rare events like hurricanes, for instance. And so developing mathematical foundations has the potential to take this really promising avenue and solidifying it. So finally, I think there are a number of different kind of broad mathematical foundational questions in machine learning that impact the sciences, but other areas as well. So for instance, imagine that we had simulated data and we want to use that simulated data for training a machine learning system. in order for this to really make sense, we have to understand things like distribution drift, because our simulated data is coming from a different distribution than real world data. We have to understand things like active learning so that we can figure out, well, what are the best simulations to run to generate my training data and to facilitate the learning task that I'm trying to accomplish. And then finally, generative models for science.
Actually, Rebecca, we are running out of time, so maybe if you could summarize.
I guess 30 seconds more of material.
All right.
So many of us are familiar with ChatGPT and DALL-E for generating text and images. We might also like to generate climate simulations or proteins. And in order to do this, we have to develop mathematical foundations that allow us to deal with much less data, with things like rare events and variations in scales and resolutions. And so overall, these general foundational questions, or in general, mathematical foundations of machine learning have the potential to be broadly impactful across different applications and domain, and have the promise of helping us develop better applications and better algorithms akin to the way understanding biology helps us improve healthcare. Thank you very much.
Okay, thank you very much for both very interesting talks. Now it's the time for questions. So we have a question from Catherine for both of you. Any advice for young researchers wishing to contribute to the math foundations of ML? For example, what areas to focus on studying? Maybe I'll start with Morgane and then Rebecca afterwards. Morgane, are you still there? Oh, she seems to have dropped off, in which case I guess, Rebecca, maybe you can answer first. Hopefully she'll come back.
Sure. So at the beginning, I think there's things like linear algebra and probability and statistics that are just relevant across the board in machine learning. And anyone just getting started should absolutely focus on those issues or on those domains. Beyond that, I think to some extent it may depend on what area you're working in, right? So I mentioned a bunch of different areas. So for some of them, you really need to understand something about PDEs and scientific computation. In other settings, maybe you really want to have a grounding in information theory or signal processing. So I think that, there's really no area of math that's untouched by modern machine learning. And a lot of it will be application specific.
Okay, so Morgane, I don't know if you caught the question. So the question was,
my connection broke for 2 minutes.
Okay, yeah. So the question is, do you have any advice for young researchers wishing to contribute to the math foundations of machine learning? Like what areas to focus on studying, for instance?
I am biased because I'm a statistician, but I think that you need to focus. I think there's a lot of tools and things that we need to understand from probability and from statistics and going back to the fundamentals. There's, I think, a lot of mathematical questions. So I heard that Rebecca mentioned PDEs, and I'm sure she mentioned optimization probably. So I will try to mention that. I think a lot of new ideas are going to be brought by other fields that have not been as used in the past to understand machine learning, because we have already exploited a lot of the tools that we already have. And so I think, for example, tools coming from, ergodic theory, from random matrix theory, pre-probability, and all of those different fields. And for example, understanding symmetry, well, you have notions of group and algebra in there, and those are very important. For example, Rebecca talked a lot about physical systems. There's a lot of symmetry there, and so I think you want to start with the foundational, and so probability, inference, information theory, and then I think maybe bringing some of those can be interesting if you want later on to. I think a lot of new ideas are going to come from those other fields also.
Okay. So I have a follow-up question to this. So in areas of theoretical computer science, like computational complexity, there are these major mathematical conjectures like P equals NP, which have been a great driver of research. Does machine learning have comparable like mathematical conjectures? I mean, Rebecca did mention some open questions, but they're not completely mathematical. I mean, they also depend sort of on other sort of non-mathematical factors. But are there like mathematical questions which one should draw attention to and be sort of seen as foci of mathematical foundational research? Maybe I'll start with Rebecca.
Yeah, that's a great question. I'm not aware of anything that's as kind of clearly and concretely stated as something like P versus NP. I do know that there are empirical observations that we've made that have led to conjectures. So for instance, one big question has been, well, what's the role of depth in a neural network? Like, why do I get better results when I increase the depth? And, some of the generalization bounds that were done in early days, like Morgan mentioned, said depth is worse. And so they were just totally vacuous and inconsistent with what we saw empirically. And so there are conjectures about the role of optimization and the way that adding more layers affects sort of the landscape of this objective function or this optimization landscape that we're trying to navigate. But it's just not as clearly stated as a formal conjecture as what you're hinting at. Morgan, I don't know if you've got better thoughts here.
I don't necessarily have one big question, but I think there's more multitude of things we don't understand. So for example, like we don't really understand how we know that the optimization, the way the algorithms are trained is crucial to what's happening, but we don't really understand how and what is actually going on. I think also there's a lot of a lot of questions if you leave a kind of a deep learning world, because there's obviously a lot of questions, and there's a lot of questions outside of that world. So example, Rebecca mentioned trying to use MRIs, and for example, we know that those were some of the first applications that were looked at, for example, coming from compressive sensing. And we know, for example, that the type of random matrices that people study in those worlds are very structured and dependent. We don't have a lot of understanding for theory on both settings. So I think there's just everywhere you look, there's kind of a gap and I'm not sure there's one big question. I mean, probably deep learning and generalization, as Rebecca mentioned, is like if someone can solve that, they have probably made a huge breakthrough. But I think there's more like also a lot of series of things that we just don't understand. And
okay. Okay, thank you. I actually have a question for you, Morgan. You mentioned in your talk that sometimes, paradoxically, training on small data sets can be more effective in some regimes than training on large data sets. Does this suggest that maybe we should actually change our training protocol sometimes to maybe first train on a small data set and then introduce a larger data set later, rather than just dump all the data at once?
Well, so this happens more like in a very critical setting. When the ratio between the complexity of your model and the number of observations is of a certain size. I would be wary of like changing the way we change things before we have a full mathematical understanding of what's going on. For those models for which we do understand, there has been suggestions on adaptively choosing the sample size. So for example, this has been like proven, for example, studied, for example, for some simple models such as regressions. And it was proven actually very interestingly that it's kind of equivalent to some regularization that the statistical world had already introduced, such as wage regression. So this kind of idea has been explored in a way, but I think it's question mark beyond, logistic regression and things where we really know what's going on.
Sorry, Maureen.
No, go ahead.
Well, yeah, I completely agree. I think one thing I might just add to that is that there is this subfield of curriculum learning where, just like with kids, you teach them how to do easy tasks before you have them grow to develop the ability to solve hard tasks. With curriculum learning, you would try to feed your machine learning system easy examples first, and then gradually increase the complexity. This is interesting, and there have been some really compelling examples of this in action. But this is another thing where I think we don't have total theoretical foundations. Like, how do we even decide before we've trained the model what makes an example easy or hard? And how do we actually make this process rigorous? I think there's a lot of interesting mathematical questions there.
Okay. So it's a question from Matt. I guess it's got to calibration. So what are the opportunities for using some sort of adversarial model where you have two different machine learning algorithms and they try to play off against each other to sort of measure each other's uncertainty? Are there ways to do things like that?
I'm not aware of that. I mean, I think that a lot of the stuff that I've seen in this space assumes that the training data and the test data are exchangeable. So for instance, independent and identically distributed. So you're going to be testing your system out on data from the same distribution as what you trained on. And so if you were to use sort of an adversarial system to generate really hard test samples, then I think that, that's an interesting idea. I don't think that we have the foundational mathematics to really understand that carefully.
Okay. Little Morgan, you're still there.
Yeah, I'm still there. I'm sorry. My connection isn't stable. There's a thunderstorm outside. I'm sorry.
Did you have anything to add to that?
No, I don't think I have anything to add. I think it's an interesting question, but no, I don't think anyone has explored that. And I don't,
Okay, in that case, maybe we'll wrap up the session because we're going to move on to the panel now. So thank you very much, both Rebecca and Morgan, for your wonderful talks and your willingness to answer questions. So we're moving on now to the challenges and barriers panel. So we're going to bring back 3 speakers from previous sessions. We have Jeremy Avigad again, who, sorry, I'm trying to pull up the bio. So he's a professor of Department of Philosophy and Department of Mathematical Sciences at Carnegie Mellon, working in mathematical logic, formal methods in mathematics, and history and philosophy. We also have coming back Ursula Martin, who just spoke a few hours ago, on an emeritus professor at Oxford and Edinburgh, working on the use of computers to create mathematical proofs and social and cultural approaches to understanding the circulation of mathematics. We also have again Stella Biderman, who was also spoke today from Booz Allen and Hamilton, who works on open AI, on open source AI and making cutting edge AI technologies more accessible. And then finally, we have a new panelist, Carlo Angiuli. So he is a postdoc at Carnegie Mellon University and incoming assistant professor at Indiana, whose research interests are in foundations of dependent type theory and programming languages with an emphasis on applications to homotopy type theory to formal verification. So the topic of this is the challenges and barriers in the road ahead to further deployment of tools, of AI type tools, machine learning type tools to further mathematics. So maybe I'll just pose a question to all of you, and then you can each in turn give a long answer or personal statement if you wish. What do you think are the common challenges faced by the community in AI-assisted math reasoning? So maybe we'll start with in order of introduction. So Jeremy, what do you think are the main challenges looking forward?
Yeah, so that's a good question. So I think, so as I explained in my talk, there are a number of communities involved. And so I think I will focus mainly on the mathematical community, the challenges to the mathematical community. And there, the issue is that this kind of research, it doesn't really have a natural home. So when it comes to, young mathematicians using formal methods, excuse me, I think the demographic of the community is, there are a few more senior people like me who have tenure and can do, have the privilege of being able to do whatever we want. There's kind of then a tier of people who are, postdocs or, pre-tenure, who are really kind of putting their careers a little bit at risk by, doing these non-standard, unusual things. And then it's really sort of a grassroots. There are a lot of young people. There are a lot of graduate students and undergraduate students who maybe just don't know what's ahead of them. But so I think the real challenge of the community is figuring out how to open up a space for the younger people in the community to succeed. The good news is that there is amazing talent and energy, and people are really smart. They're enthusiastic. There's a lot of excitement. There's a feeling that here is a technology that can really do a lot for mathematics. That there's a lot to contribute, and it's not really clear what the standard path is. I think in the short term, for young people in the field, they still have to establish themselves by working in traditional areas of mathematics and writing traditional PhD theses. But in the short term, there's a hope that, if part of their work involves formalizing, contributing to a formal library in the area, or formalizing some of their work, or experimenting with automated reasoning tools in their area, the hope is that that will be valued and that will count towards, hiring decisions and promotion decisions. So I think the main challenge is really an institutional challenge to get the field going.
Okay, thank you. So Ursula, what are your thoughts on the challenges and barriers ahead? You're muted.
I should have learned after 3 years. Right. Well, as so often, I listen to what Jeremy has said, and I think, gosh, Jeremy, you've said it all. What else can I say? But I think a lot of it is institutional barriers, but that kind. But I think we should maybe look to other examples. So, for example, numerical. I'm not sure if you call it numerical computation in the US, but people doing mathematical modeling using MATLAB, using R, using massive tools like that. In the UK, that's very well established as part of a mathematical endeavor, but it's been driven by a lot of other activity. For example, those groups go out and form external partnerships. There's nothing like a lot of external money to make it. I used to be a dean, so I can say this. There's nothing like a lot of external money to make a dean kind of wake up, and start looking at the world differently. So, one can have a tradition of specialized units who are rewarded. One can have a tradition of people being seconded to companies and things like that. So I think there are those kinds of barriers which one can get over if one, not in every institution all the time, but if one thinks of institutions who are taking this seriously, like your own, Jeremy. But then I think the other thing is thinking about how these technologies actually fit into the mathematical pipeline. So in the gap after my talk, I was looking up, unfortunately, it's a rather old correspondence I had with Peter Sewell in Cambridge about Popple, and I don't have up-to-date data on this, but there was a time, or maybe it's still the case now, where Popple was certainly encouraging people to do formalizations as an appendix as part of Popple papers. And it wasn't compulsory, but people were doing it. If you look at some of the example I put, if you look at, there are pieces of math that you could verify, but embed it in a broader paper. And I think that sometimes, similarly, that is how verification techniques have been taken up in industry. So, for example, the people, what was the system called? Anyway, there's a group in London who went to work for Facebook. They developed bug checking software, and that was based on separation logic. But they were hired into Facebook to work on a particular aspect of the development pipeline in Facebook. There was no sense that suddenly Facebook were going to drop their entire development pipeline to do what these guys were doing. Well, of course, there's probably people from Facebook here, but of course they weren't. But what they were going to do was find a place for this technology to sit as part of the regular workflow. And I think one can look for opportunities of that kind. Of course, that doesn't solve the problem of there's an awful lot of infrastructure to support that, and how is that going to be rewarded? Does one have a structure of paying people as research software engineers, we call them in the UK, to help do the heavy lifting of some of the development? Does that feed into? So I think if one goes into it, there's a great tradition of getting gloomy and sitting there and saying nobody uses our stuff, blah 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 blah. But I think you have to go past that and look at how things have worked for other disciplines or other sub-disciplines, and look for opportunities and see how you develop that.
Okay, thank you. So Stella, what are your thoughts on the challenges and barriers ahead for AI in mathematics?
So speaking on behalf of AI researchers, I think the biggest barrier is that we don't know what y'all want. We don't know what would be helpful to you, what wouldn't be helpful to you. Speaking for my own institution, I have a lot of competing resources. I have a lot of people who are experts at working with and fine-tuning large language models. If there are problems that people come to us and say, you know, here's a thing that we think might be able to be done with a large language model, and if we can do that, that's going to make our lives better. It's going to be something we can use in our research, and also will help you kind of, you know, collect the necessary data, and also that, you know, we'll help you collect the necessary data and you know, give a mathematically informed opinion and advice along the way. We'd be thrilled to do that, and I think that that is true at several, if not many, AI organizations as well.
Okay. So Carlo, you're next, and actually, if you since you're new, maybe you can also spend a minute to introduce yourself.
Sure. Yeah. So, well, like you said in my bio, so I'm a computer scientist who talks a lot to mathematicians, I guess I would say. So I work on proof assistance, and particularly on the kind of mathematical and logical foundations of proof assistance for verifying software. So I'm particularly interested in something called homotopy type theory that builds in a lot of kind of ideas coming from mathematics to kind of make proof assistance more powerful at expressing certain kinds of reasoning. So maybe you wouldn't be surprised to hear that basically I agree with everything Jeremy said at the start. I think maybe just to put a finer point on it, I think one way to think about what he was saying is basically does using a proof assistant for math, or does using AI in any way for math count as math in some very I don't mean that in the sense that I'm gatekeeping, but I mean, you can ask questions like, do these results or techniques get published in math journals or in CS journals or AI journals or whatever? And this affects, you know, whether the people who work at the intersection of these areas are going to find their way into math departments or CS departments. I mean, or maybe no departments, but I mean, it's, you know, for example, if you just take some mathematical theorem and you, that's, say, well-known, and you formalize it, I mean, the current situation is that you probably can't, just to oversimplify, you probably can't publish that in a math journal, but you could publish it in a sort of CS venue for, you know, especially one for proof assistance, potentially even a, you know, a very good one. Maybe another angle on a similar topic is that a lot of the speakers have talked about, you know, the importance of collaborations between mathematicians and experts in AI and ML. And of course, I think that's a good thing to do, but maybe to set our sights toward the future, one thing to wonder is, what would it look like for mathematicians to be able to use AI techniques in their research without a really, you know, strong, constant collaboration with an expert in AI. So I think one thing that Jeremy's group in Lean have done a very good job with is finding a way of making a proof assistant something that a mathematician can use without needing to have, you know, an expert in proof assistance next door to them. Now, of course, they need to go on Zulip and ask a lot of questions, and maybe, you know, it helps to communicate with these with experts, but eventually they can kind of start doing some things on their own. And I think if we want AI techniques to, you know, continue to take off, these are kind of two aspects of the same problem that we really have to think about. What would it take for AI to just be part of math somehow, rather than part of AI only?
Okay.
There's something I want to interject here, which is as we talk about incentive structures and getting the right payoffs and stuff. For me, there's an elephant in the room, but I don't know if this is maybe on the radar of all of the mathematicians here. If you do AI work, you get cited a lot, like astronomically more than the overwhelming majority of mathematicians. If a PhD student is concerned about whether doing like AI for math stuff is going to be something that they can use to build a career out, that largely comes down to what exactly the metrics departments are going to be looking for in mathematics departments are. Is it, if you have 1,000 citations, but they're in tier 1 computer science venues instead of tier 1 mathematics venues, the analysis of mathematics and whatnot, is that going to be a problem for you? And I mean, like the number 1,000 is not even a exaggeration. If anything, it's likely an understatement. A PhD student who works in this area in publishes in AI venues for 3-4 years can easily amass well over 1,000 citations. I've been an active researcher in large-scale AI for 2.5 years, and I have like 3,000 citations so far, which is astronomically huge numbers by standards of most fields of mathematics. But
So
the cost of.
So if I could weigh in, I was going to say that I don't think I've ever seen an academic field in which citations count less than in pure mathematics. Pure mathematics, the judgment is really on the difficulty and the challenge. And almost if a paper has too many citations, I mean, the idea, the point is some of the most difficult and challenging mathematics is understood by very few people. It's very, very narrow field at the forefront of mathematics. And so the feeling is if you have too many citations, it can't be all that hard. So it almost works in the other direction. So I agree that Estelle, you've got it absolutely right. The question is, what are the kind of the measures of success and so on. And maybe in mathematics they should count. The citation counts should count more. But the mindset is really not. It's really more the judgment of it's which journals you get into rather than how many citations you have.
Yeah, that's really interesting to hear, because in AI, it's almost the other way around. My most cited paper of all time is not published anywhere. It's an archive preprint. It has like 400 citations, 500 citations, something like that. And there are a large number of extraordinarily influential papers that never got published. Formally in an academic venue in AI, the paper describing the GTB2 model, this paper describing the GTB3 model was eventually published like close to a year later from when it was actually released online. And so there's almost the opposite incentive structure in AI where, yes, getting accepted into top tier venues is definitely beneficial. But if you have an archive preprint that has several hundred citations and people all over the world using your system or building on your ideas, like nobody cares if it never gets published, or at least a lot of people don't care.
Okay, Ursula, you have a response?
Yes. Well, yes. One thing I was thinking about an analogy actually, which was, is Moshi still on the call? Moshi isn't here anymore, but Moshi may remember chapter and verse of this better than I do. But a few years ago, there was some concern that computer science departments in the US were not paying enough attention to computer systems research. And one of the reasons for that was because computer systems researchers at the time often published in workshops and conferences. It was felt to be low status and blah, blah, blah. And so what happened was a group of the great and the good, the computer science equivalent of Terry and Jeremy and people like that were convened by somebody like the ACM to write a report, or to write a report, which was then used to influence people. And so what happened was this was a kind of top-down approach of saying, okay, deans everywhere, heads of department everywhere, you've got to listen to this because, and the kind of arguments that deans and heads of department listen to are generally about either money or talent. You're losing talent because you're not recognizing this burgeoning area of research, which is incredibly important to blah, blah, blah company. And by the way, if you start recognizing these researchers, money will flow into your department. And so, you know, I think there has to be a political dimension. Perhaps it's happening already, of doing this sort of thing. And the fact that we are here today, that this thing is sponsored by the National Academy of Science, the fact that we do have senior mathematicians, Fields Medal winners and whatever, paying attention, all of that adds just to that. Now, of course, that's not so much comfort. If you're a junior scholar saying, oh my Lord, I've got to wait 5 years for all this politics to happen, you might say, well, I'm going to get on with my life and go get a job doing something else. But you know, there has to be that kind of high-level leadership, because if it's not happening, then, you know, you can be sure some other lobby group will be lobbying and will be lobbying, and one will get forgotten.
I don't know, Carla, did you want to say something earlier, or?
Oh yeah, no. Just to Stella's point, I wanted to say that I think the risk with, if somebody has, you know, AI publications with thousands of citations and they show up to a math department, I think the reaction might be, okay, well, you seem like a really good researcher who just isn't a mathematician, right? And so I think, I mean, there is an issue, and I mean, we see this in interdisciplinary areas, a lot of like where the kinds of venues that people publish in are different between different disciplines, and the number of citations is different, but I think many of us, and I certainly have had, you know, this issue to some extent, have struggled primarily with just convincing people, you know, that we really do work in some particular area, you know, not just that we're good at what we do, right?
Yeah.
Hopefully the culture changes and what the definition of what mathematics is becomes broader. That has been a general trend I found, so hopefully the future is be better. I have a question from Eric, aimed at Stella, but maybe other panelists can weigh in after. Because of the large sums of money required to train models, there has been a drastic shift of researchers working in public institutions to private ones. Is this a solvable problem? And if so, how do we overcome it?
Yeah, this is a huge issue. And it's not just the money, though that is one of the key factors. Another key factor is training. I had mentioned this a little bit, I don't know if you attended my talk earlier, but the kinds of stuff you need to know to train like a 10 or 20 billion predator large language model, which is kind of the close to, but not actually at the state of the art for what's been publicly released so far, just isn't something that your typical CS PhD student is able to get, even in an AI department, even in a department that does a lot of research using these kinds of models. And so what they do is they go do summer internships at Google or OpenAI or wherever, and they work with a research group and get trained by that research group, and typically go and work there because that's where they know people, that's where they have connections, that, you know, and so there's a huge drain from academia into large corporations in terms of large scale AI research, both at the, you know, if you're a professor and you want to be doing this kind of stuff, that's how you go get involved. But also in terms of the foundational talent, most of the students who have the most experience doing stuff like this don't stay and look for computer science professorships.
Okay. Does anyone want to add anything to Stella's response?
I would. So I agree with the concern. So in my session, my fellow speaker was Al-Hussein Fawzi, who talked about his experiences at DeepMind, which seems to be very good at supporting fundamental and foundational research. I grew up in the heyday of AT&T, Bell Labs, and IBM, where there were corporate entities with very good mathematical research groups. But I think that's becoming unusually, especially rare right now. And I think for pure mathematical research, I think, by far the best environment is an academic environment. I mean, what makes mathematics special is having the freedom to just explore ideas, wherever they take you, and not concerned about, what's the application, what's the bottom line. And so, yeah, I mean, if the sort of outflux of kind of resources and money is going to companies and corporations and talent, I think that's dangerous for mathematics. Mathematics, I think, will always the primary home will always be in the university, and we need to make sure that it has the resources there to do the things that we want mathematicians to be able to do.
This is just a general comment. Stella, I loved your talk. And in particular, what I wanted to do was bottle it, well, it could be online, and send it to a group of people in the UK who are lobbying, you may have heard about this, who are lobbying for the UK to have a sovereign AI capability to match what you were describing. And the sums of money being talked about, you just feel sad when you look at the numbers you were talking about, it's, nobody's thought this through, but they're lobbying very hard. And because our politicians don't understand the technology, don't understand big numbers, but sort of think AI is sexy and cool, they're kind of backing it in a way that is almost a public embarrassment. But yes, thank you for spelling all that out so very clearly. What the challenges were.
Carlo, you want to say
Thank
something?
you.
Yeah, I actually have kind of a follow-up question for Stella. So I think in some places where CS and math intersect, you can see that CS departments and grants often are larger, right? They have more money than math departments. But it kind of sounds like at the scale of the issues that you're talking about, even the CS departments don't have enough money. It's really just a matter of like industry versus academia. Do you think that's true, or?
I wouldn't say it's not that they don't have the money so much as the political will to spend the money. People throw around $1 million, $5 million. That's definitely a lot of money. I'm not going to say it's not a lot of money, but it's not like a mind-boggling amount of money. That is the amount of money that one can win in a government grant. That is an amount of money that most, like any Fortune 500 company can afford to train their own 20 billion parameter language model. The overwhelming majority of them choose not to because they don't think it's a good use of their money, but it's not like they don't have the money. Concretely, there's a bit of a challenge in terms of, if you're an academic trying to get the kinds of grants that you need to train models like this. In the United States, we have supercomputers that are reasonably well suited to doing this, not phenomenally, but reasonably well suited to doing this. But winning grants on those supercomputers to do pure AI research is very challenging. So Oak Ridge National Lab, for example, has a annual grant process where they give out, I want to say like hundreds of millions of GPU hours to about 60 or so different organizations that apply for grants. And me and my collaborators at Mila and a nonprofit in Germany called Lion actually won a grant for 6 million V100 hours, which is enough to train like a really good language model. We've used that to do some really impressive research. We were the only people who won a grant to do AI research for the sake of AI research. There were other groups using AI to do biomedical research, to do climatology research, but we were out of the 60-ish people who won grants, the only people who actually won a grant to just train AI systems and develop AI capabilities. And so, the computing resources are there. They are owned by governments. I'm not as familiar with supercomputer access in other countries, but the French government sponsored the training of one of the largest language models in the world, on the Shanzai supercomputer. So the resources are, from a computing point of view, are actually there. They're just difficult to obtain or difficult to spend. It seems challenging to you might be able to win a several $1 million NSF grant, but can you win a several $1 million NSF grant where they let you spend the vast majority of the money on computing resources? Like that's a question about, having what I think of it mostly as being about the political will to actually spend the money, or getting access to it than it not existing in the first place.
So there's a related question from Lars. Where do you see the funding coming from for AI and math, automated theory improving, and interactive theory improving going forward? It seems like a main funder so far has been Microsoft, and mostly just Microsoft. Anyone?
Google's been funding a lot of this stuff. Talia can speak to that personally. They've worked on a really cool project that I kind of lambasted at Google. DARPA funds stuff like this. That's another place where you can get funding for this kind of work. It seems to me to be mostly difficult to find the opportunities. Like they do exist from a variety of different organizations, but finding them is challenging.
Okay. All right. If there's no further comments, we'll move on. So Patricia asks, PhD students in pure math usually have a limited coding background compared to CS students. Do any of you have any suggestions or projects for students to engage with AI tools, considering the limited time frame of a graduate program?
So I certainly have one. So first of all, I think that's changing, by the way. So a lot, again, the younger generation is kind of growing up with a facility with computing. Even mathematicians, young math majors are growing up with a facility with computers that it's really it's built into the way of thinking. So a lot of young mathematicians do have good computing skills. And if you want to get into formalization, just go to the Lean Willett webpage, introduce yourself, ask around, and there's endless bits of math out there to formalize. There are lots of things to do. You'll get help and support. So yeah, there are lots of ways for people to get started and learn what they need to know.
Although I do think it is, so I agree with everything you said, but I think that it is unrealistic to imagine that PhD students in math would, end up knowing enough about about AI and these systems to do, some of what some of the experts have been talking about, over the past 2 days stuff. So that's why, again, I think that certainly some fluency with using computers and using these models is important and definitely learnable. I just that's why I mentioned earlier, what would it take for a non-expert, maybe just somebody with a moderate coding skills to engage with this stuff.
Yeah, I mean, to be clear, I think there's a general consensus that what we really need are very tight collaborations between computer scientists and mathematicians, bringing the different skills and working together. Yeah.
Okay. You definitely can work with like smaller models. So I keep measuring models in terms of a size that measures the number of parameters. So models with like single-digit billion parameters are something that you can train in single GPU that don't require a huge amount of expertise, and there are libraries that will just run that out of the box pretty much. Where most of the work that you would put in goes to choosing the right configuration options and collecting the data and not really having to write almost any code at all. Honestly, based on my experience talking to people with math PhDs, the number one piece of advice I can give is go audit CS 101 for non-majors and learn how to code in Python.
Okay.
Yeah, that's the kind of thing that an awful lot of math students do now. Either formally something as taking something as part of their program, or just learning anyway on the side, just because they feel they feel they'll be lacking a part of their education or their university experience if they haven't learned to code in some way.
Yeah, that's increasingly important. Yeah, I definitely recommend it to my own students. So this ties in a little bit with a question of Talia. One of the scariest things about collaborating with AI or machine learning folks is that the community is so large and powerful that you often end up needing to do everything on their terms. Is there some way we can just address this power dynamic? Is anyone brave enough to touch that question?
I don't have an answer except the classic one of saying, I think that is a really good question. But of course, the next point that Talia is making, sorry, I'm looking at the chat, is that it all depends on who you know. But it is the case, any particular interaction won't be with that big, vast, powerful AI community. It will be with particular individuals you're working with in a particular company, or a group of you are working with in a particular company. I mean, on the first day we heard about the Geordie Williamson collaboration, and I mean that one strikes me. Here we have a top mathematician working with. My guess is he was working with people who were highly mathematically trained. It was people who weren't there. This is Geordie talking about finding conjectures in not theory. And I think that I mean, my experience is a rule that applies to any kind of collaboration. You need to find the right collaborator, and sometimes it can take a little while. And it can always be a learning experience to try and collaborate with the wrong collaborator. If your meetings, if you've had 3 meetings and you end up feeling miserable, it's not you, it's not them. It's just, this was not meant to be. It's like dating, you have to find, and it can be worth, your instincts begin to hone, and then finding the right collaborator is an enormous part of the battle, and finding and that's why opportunities to experience what's going on at companies, or going to conferences or workshops in the days when we used to go in person and and actually get to meet people, I think is it's important, because also the wrong collaboration can just be rather disheartening. And I'm sure any educator has had the experience. If you have a summer student who's somehow they were highly qualified, but it's not working, and you think, well, I've only got 6 weeks to make this work, and give them some kind of valid educational experience, because it's about them, even if they're not going to do anything that's remotely useful to me. I want them to have a valid educational experience. And so I think it's there's a lot there about, it's not really an answer to your question, except saying just because it didn't work once, it doesn't mean it won't work again. Too easy to fall into dating metaphors, sorry.
Yeah.
One thing I want to say in response, sorry.
No, go ahead, Stella.
So one thing I want to say in response to that, and this is probably worth clarifying, might not be terminology that the audience is super familiar with. When I talk about the costs and challenges associated with training very large language models, I mean producing what are now called like base or foundation models. Oftentimes when you want to go use them, it requires several orders of magnitude less compute and less money, and can be done sometimes even on commercial devices that you can get in a fancy personal laptop. There is a huge and booming community of random people on the internet. There are several large and booming communities of random people on the internet doing really high quality AI research on not developing like new foundation models, but fine tuning them, evaluating their applications, using them in new ways, and adapting them to new application areas. There are people doing this out of passion and interest in organizing in Discord servers. Like a lot of the cutting edge of large language models research that doesn't happen at large tech companies nowadays happens on Discord, which is really one hell of a sentence. But there's a lot of communities out there and a lot of places to find collaborators that are not, the corporate giants or Turing Award winners or whatever.
Yeah, so if I could add something, I mean, this is kind of a roundabout response to Talia's question, but we opened this session with, with a discussion of the big challenges, and we focused a lot on the institutional challenges of, supporting people who want to work in the area and, making sure that they can, have a livelihood. But I think the second biggest challenge is crossing the disciplinary boundaries. And there's certainly an institutional side to that. I mean, if you're in a computer science department, you're expected to do certain things. And if you're in a mathematics department, you're expected to do certain things. But there's also a very large social component. I mean, I've had a wonderful career where I've had the opportunity to go to conferences in mathematics and computer science and in philosophy. And, you could have a sociologist field day of just kind of, trying to explain the differences between the community, how people think, how they talk, what they expect. And so one of the reasons that collaboration is hard is that, mathematicians don't know how to talk to computer scientists, and computer scientists don't know how to, it's just awkward. It's just the mindsets are so very different, and you can get past it, but it's, it really takes a lot.
That's why, it takes time, and anything that takes more time, people will start to view as a risk, just because they think, well, I could be spending that time doing other things.
It's always easiest to fall back on. It's always easiest to fall back on the things you're comfortable with and that So it's hard to go out on a limb.
It is worth noting that events like this do make these things easier. So I have been heavily promoting this event. Talia has as well inside my open source research community. And I've had several AI people come to me and be like, I didn't really know what mathematicians did that made them different from computer scientists. And talking about how, they, the specific talk that multiple people called out as being really informative was about what makes mathematical knowledge different, and how, how you can prove something without knowing really anything. Prove something by looking at formal structure. Just the idea of mathematical proof is not something that every undergraduate gets exposed to. At some universities, you certainly would, but not everyone, especially people who are computer science or other non-math majors, may not even get exposed to that. And so a lot of the people walking around in the AI world today don't really know what mathematicians actually do. And I can speak to the fact that this event has at least, helped close those barriers a little bit, because they've been learning by watching it.
Yeah, and hopefully there'll be a follow-up in-person event that would actually also greatly strengthen these sort of social connections. So Jeremy and I and some other organizers, we actually organized an in-person event at IPAB at UCLA earlier this year on machine-assisted proof. And I think it did bring a lot of communities together, and there was a lot of emphasis on socialization, which I think really did go a long way towards making these connections. Okay, so Petros actually has a question.
Yeah, as coming, I'm not a mathematician, I'm not a computer scientist, and I think I'm somewhere in between as a computational scientist. But since we have this discussion about mathematics and computer science, these two fields, long time ago, they were coming from the same tree somehow, and before they split into two different branches, if you like. Is this AI a possible place where this split can be eliminated, or it's going to become even bigger? How do people see that? I mean, another way to put it is, why should computer scientists, it's the century of computer science, why should they bother about mathematics? That's a provocative way of putting it.
It's fun. I mean, computer scientists build systems that study non-computer science things all the time. Like most of AI is not about, even when we talk about quote unquote pure AI research, it's usually about a handful of applications that AI researchers have accepted as like, core applications: natural language processing, image classification. So, I mean, a large part of doing AI research simply is building systems that operate on data from the real world, from other domains that you may not have a strong expertise in. And there are people who just find it inherently interesting to study the question of applying AI to mathematics, just like there are who study the question of applying AI to studying natural language.
Responses? Okay.
I think there are a lot of domains where computer science and mathematics can come together. And as I said in my talk, just broadly speaking, you know, we have to remember. I mean, mathematicians have to remember that one of the reasons it's so enjoyable to explore ideas is that we have the sense that these ideas enable us to do things, and one of the reasons that we can do all the things that we can do is that we can think about them. So I think overall it's healthy for the communities to come together in lots of areas where you need theory, you need implementation, you need engineering. You know, you need high-level theory, you need low-level engineering, you need everything in between. So any opportunities where the fields can come together, I think, is good.
Yeah, and I think that, you know, verifying software is kind of a nice microcosm of this, where, you know, even if all you care about is making sure that, you know, your plane doesn't crash, right? You have to, when you verify the software, you have to verify a bunch of mathematical theorems, you know, at the same time as part of doing that. And so I think it's very natural that these all these ideas kind of meet.
Okay.
There's also a moderate overlap between at least part of the AI community and part of the theoretical computer science community. So there's a kind of joint conference between the theoretical computer science and mathematics and AI communities. I know plenty of AI researchers who go and write theoretical computer science study, like complexity theory style papers, and publish them at theoretical computer science venues. And, you know, that's an area that has a long history of closely collaborating with mathematicians and mathematics as a field. It could also be a particular way of thinking about, you know, bringing different fields together.
Thank you. The next question is from John. Are there any ethical issues involved when researching the interplay of mathematical reasoning and AI? For example, are there any inherent dangers with AI having capable or better mathematical reasoning than humans?
Gosh. Well, there can be ethical issues. In the training. I mean, the ethical issues in training AI. But you know, that's the ethical issues in the building of the underlying systems. It will partly depend what people were using it for, I guess.
I think that mathematics is probably one of these. I mean, like there are a lot of ethical issues with the development of various AI technologies, various applications of AI technologies. I think that applying AI to mathematics is one of the safest ones from an ethical point of view. You know, there was a big scandal. Scandal might not be the right word, but a big realization in the AI community not too long ago, where for many years there were researchers who were publishing kind of like very specific computer vision type problems about how do you identify someone the second time they come back into a video frame, and how do you and do stuff like that and track them and be able to distinguish between them even when they're off camera. And it, you know, later people became aware that most of these people were living in oppressive regimes that were explicitly deploying these technologies to surveil their own citizens. And a lot of AI people from the United States didn't really realize this at the time, that this was kind of the motivating impetus for doing this work. But we see this in the United States too. We see algorithms being used to decide who to arrest by police. There's a huge, you know, this is just one example. You can pull up examples with natural language processing. You pull up examples with almost any application of AI. So in that regard, you know, I look at AI for mathematics and think like, wow, you know, it's really hard to accidentally contribute to a system of oppression or something that's going to be abused and misused if what you're doing is writing theorem provers, comparatively to all of the other things you could be doing with AI.
Hopefully, at least. Okay.
Yeah.
So I like Stella's answer very much. I just mentioned there's a famous quote by Rudolf Carnap that in logic there are no morals. So.
Well, it's still the case at the AMS meeting in Boston this January. There was a bunch of people protesting against the NSA, that was called, isn't it? Yeah, the NSA, who were who were removed. I mean, there are people with strong opinions on this. So.
Yeah, and I mean, there's still the fact that the mathematics community is made up of people. So, I mean, if for example, not to give people ideas, but like if you were to, generate a bunch of conjectures and then use ChatGPT to write, zillions of math papers and submit them to all sorts of math journals, there are kind of issues with the interfacing between, the abstract math and the real people who are helping run our communities, right? That could potentially, be problematic.
Yeah, absolutely. I just want to clarify that I didn't mean that there weren't ethical issues. I meant that it's much harder to there are fewer. That there are certain classes of ethical issues that are very common in NLP, in that's natural language processing, analyzing text, and computer vision, in other kind of mainstream fields of AI that are substantially reduced, if not removed, from doing it for math. So it's not necessarily that it's not or can't be unethical, but that I think there's a lot less of a moral hazard working in this subfield in particular.
I think it's good to be mindful. I think G.H. Hardy was very proud of working in number theory as a field that had no possible application whatsoever. And then it was horrified when it became fundamental to cryptography, which had a lot of military applications. And
yeah, I guess I'll also just add that, I mean, in verification of software and hardware, I mean, there is a lot of funding that comes from, defense, like especially, the Air Force, other things, some, DARPA, as people mentioned. I mean, there are people who, receive money to verify like unmanned drones and things like this that some people, I mean, there's actually, even in theorem provers, which you would think, well, it's just, proving mathematical theorems, what could go wrong? But there are already a lot of, people in that area who don't feel comfortable with what some others are accepting money to do.
In comparing computer science and mathematics, the computer scientists sometimes they have all these fancy applications like AlphaFold, playing poker, solving the game of Go, all these different things that they're solving and advertising. Is there something like that, like a landmark problem that mathematicians can go and say, look, we've done that together with AI in order to attract interest, possible funding? I don't know if that's relevant, but maybe just to put a flag on some mountain, as computer scientists do everywhere these days.
Well, Jeremy, are you involved in the IMO Grand Challenge?
No, I'm not. I mean, but I was going to say that I think mathematicians will value progress, using AI on any traditionally recognized mathematical problem. I mean, the reason that the work by Jordy Williamson and Mark Lackenby and Adam Wagner is so striking is that they've addressed traditional problems in mathematics. I mean, Jordy was working in representation theory and Kazan-Lustig polynomials, which people know. I mean, these are natural questions. So, I mean, any mathematical problem, anywhere that AI can make inroads, I think will be valued. And then the question is, where is that? What are the branches of mathematics where we're likely to see big successes with AI? And I think the short answer to that is we don't know. You just have to try it. I mean, we have to get the tools in the hands of mathematicians. We have to have mathematicians working with computer scientists to figure out what the technology can do, what it's good at, and whatever mathematical successes we get are going to be the measures of success.
You need some key mathematicians who are willing to try some crazy ideas.
Yeah. One nice thing is that I often feel that there's an asymmetry here between mathematicians taking mathematical ideas and using it to advance AI, and mathematicians taking AI ideas and using it to advance mathematics. And historically, mathematics as a field has thought much higher of one of these than the other. And so if you're taking mathematical ideas and trying to apply them to AI, there's definitely a question about how can you do that in a way that you can pull back and you can frame as a mathematical contribution. in representation theory in particular, I'm not familiar with the specific work that you were talking about, but in representation theory in particular, there's a huge amount of computational representation theory research going on in AI right now, because representation theory is kind of key to embedding equivariances into the architecture of a model. So if your model doesn't have to learn that proteins are invariant, if you can custom build your model, so it's automatically going to be invariant to rotation in the XY plane. That's really useful for training a protein folding model, because that's a piece of a large, complicated dynamical system that the model doesn't have to learn. And there's a huge amount of like computational representation theory work going on in particular, that I think is likely to be something that can be pulled back to or reclaimed by mathematics at some point. But absolutely, I'm excited to see what other things like that start to blossom.
Oh, Ursula, you're muted if you
One of the lovely things about this workshop is learning about things I had no idea about. So I had no idea. This is really good old-fashioned representation theory, group representation theory, so to speak. Wow.
Yeah. So one of the key core AI algorithms are called convolutional neural networks. And the original design was kind of like abstractly inspired by mathematical convolutions. But then people later realized, Rishi Condor at the University of Chicago, Max Welling at somewhere in Switzerland that I'm blanking on right now, Taco Cohen, one of his PhD students, realized that there was like an exact equivalency between a particular generalization of this neural network architecture and like honest to God mathematical convolutions on arbitrary, like really compact groups. And that you could prove that, they could learn exactly the functions that are representable as mapping from a certain type of group to another type of group. And that's really caused a huge explosion in this area of research.
Wow.
Okay. As always with these panels, we always wish they could go on forever, but we're actually out of time, unfortunately. But thank you very much to all the panelists for all their insightful comments and willingness to take questions. And I'll now pass it over to Petros to close today's session.
Thank you very much, Terry. I think we had another day of fireworks and great discussions. It has been a fantastic range of problems, opinions, and new frontiers that people identify. We're having one last day of this workshop tomorrow, so please join us again at 10 a.m. at the same address. And I wish everybody a great afternoon.